Hi guys, up to now what we were doing to solve any circuit, we were trying to write some equations either by the means of mesh analysis or by means of nodal analysis. In mesh analysis what we were doing is we were selecting some loop currents and then we determined branch currents. Branch current was current in each branch in terms of loop current, and then we applied KVL to determine the independent set of equation which we can solve in order to determine the solution of the circuit. In nodal what we assumed was the node voltages, and based on that we wrote the branch currents and then we applied KCL. Okay. But when it comes to large network, then forming such kind of equations manually is not possible. Okay. For large network, what we actually need is we need computer solution. Okay. And for computer solution, we need to write equations in such a form which is easier by the computer to comprehend. Okay. Or we can say computer friendly. In that case, we make use of network topology or graph theory. In graph theory, actually we define certain matrices by which the computer can easily analyze any network for its solution. Now, what is a graph actually? It is basically the skeleton of the network. It shows the arrangement of various components in the network. It does not give the value of any component. It does not give the nature of any component, whether it is resistor, inductor or capacitor, just how the network looks like or how the elements in a network are arranged. Okay. So while drawing any graph, we do not show any element. Okay. And we will show no sources. That is why voltage source will be short circuited, current source will be open circuited. So let me show you by an example how to draw the graph of a network. Suppose this network is given to me which consists of various components like inductor, capacitor, resistor, voltage source. I want to draw the graph. So here we have 4 nodes, 1, 2, 3 and this one. This one will be called as reference node. So first we will draw these nodes A, B, C, D. Now what you do is you replace every element by a straight line. Between A and B we have a 2 ohm resistor. This will be represented by a straight line like this. Between B and C we have a capacitor. This will again be represented by a straight line. Between B and D another capacitor. Another straight line. Between C and D an inductor. Straight line. Between A and D we have a resistor as well as a voltage source. We will short circuit the voltage source. So it will be like this. Between A and C we have a 6J inductor. Again a straight line. So that is how we draw the graph of a network in which each node is known as vertex and each branch is known as edge. So here nodes will be known as vertices and branch will be known as edges. Okay. So that is how you can draw the graph of any network. Just replace each and every element by a straight line. Now there are certain terms which are defined in reference to the graphs. First such term is known as path. A path is basically traversal from one node to another node without crossing any node twice. How? Let me say A, B, C, D. The graph that we just drawn. Now suppose I go from A to C something like this. A to B, B to C, like this. Now I go like A, B, C, A, D, C. That is, I went like this. Okay. But in this process, if you see, I crossed a node twice. Okay. So that means this is not defined as a path. Okay. Whenever you are drawing any path, you have to take care you do not cross any node twice. So what will be the valid path in going from A to C? It will be A, B, C. It is a valid path. If you want to go like this, A, B, D, C, it is again a valid path. But take care, one subscript only appear once. That is how you have to find out which is a path and which is not a path. Okay. Next term that we defined is called as subgraph. As the name suggests, it is part of a graph. Okay. If we don't draw a complete graph, rather draw only some of its branches, then it is known as subgraph. A subgraph even may be drawn as a single branch in a network. So the graph that we just drawn, like this, what will be the subgraph? A, B, C, D. This is a subgraph. This is a subgraph. This is again a subgraph. So like this you can draw as many subgraphs as possible. Just select some specific branches in a network and each such set will represent a subgraph. So a subgraph is nothing but it is collection of some of the branches of a network, not necessary in any fashion. Okay. There is no rule to determine whether it is a subgraph or not. If it consists some of the branches of the network or some of the branches of a graph, then it will be classified as subgraph. And even it is not that there should be no closed loop, this will also be a subgraph. So do not take it for granted that there should be no closed loop. There can be closed loop in a subgraph. Is it fine? The next term we define is known as directed graph. Now what is a directed graph? In a directed graph what we do is we give a reference direction to each branch of a network. How to give the direction? That direction can be random. It does not necessarily indicate the direction of flow of the current. Okay. Like the graph that we had just drawn. We can give these branches any direction that we like this. Any direction. This is a directed graph. Okay. You may even change the directions. Like this. Then also it is a directed graph. So these directions are not predefined. These are as per the user choice. But this gave us a reference direction so that we will say if any quantity is in flowing or if the current is flowing in the opposite direction to the reference direction, it will be considered as negative. It is just like the mesh analysis. The direction of loop current that you assume is as per your choice. That does not depend on how the source is connected or how the load is connected. That is purely by choice. But even in control systems we studied something called as signal flow graph. Okay. There the direction actually indicates the direction of signal flow. Okay. There the direction is not random. But when we talk about networks, here the direction is random. you can take any reference direction as you want. This direction does not have any physical significance. The next term we define is connected and a complete graph. So first of all, what is a connected graph? As the name suggests, all nodes are connected to each other. That is, there must be some path to go from one node to the other node. Like this. Now you can travel from one node to another node as you may want. Like if I want to go from A to C, I can go like this: ABC, ADC, ABDC. If you want to go from C to D, you can go like CD, you can go like CBD, CAD, any way you like. B to D, direct path BD, BAD, BCD. Like this you can travel from one node to another node in whatever path you may like. That is known as connected path. That is, there is always a path between any two nodes. Now what is a complete graph? In complete graph, there should be a direct path between every pair of nodes. That is, every pair of nodes must be connected by a branch at least. Okay? Like if you see, while going from A to C, there is no direct path. ABC, ADC, ABDC, you have to pass through one additional node. But if there is a direct path between A to C as well, then it will be a complete graph. So this graph is actually a complete graph. Here you can even travel from A to C directly. Here C to D direct path, B to D direct path, A to B direct path is there. So there must be a direct path between any two pair of nodes, or we can say that there is a branch between any two set of nodes. Okay. Now, how you can make a graph complete? Whenever you will choose any two nodes, you have to put a branch there. So number of branches will be how much? NC2. Okay. Because between any two between any two nodes there must be a branch. So how many ways are there to select two nodes out of n nodes? That is NC2. Now suppose there are 5 nodes. Then what will be the case? 5C2, that is equal to 5 into 4 by 2, that is 10. In our case there are 4 nodes, so it will be 4C2, that is 6. As you can see, 1, 2, 3, 4, 5, 6. We have 6 branches, that will make it a complete graph. So remember this expression: to make a complete graph, you need NC2 number of branches. The next term we define is a tree and a co-tree. This tree is very important because our further analysis of the graph theory or any network will be based on these trees. What is a tree actually? A tree is nothing but it is a subgraph, but no closed loops. I told you any part of a graph can be said to be a subgraph, and there is no restriction whether there should be closed loop or there should be no closed loop. Closed loops can be present, but only those set of subgraphs in which there are no loops and still all the nodes are connected to each other. That means all the nodes are connected to at least one branch without forming any closed loop will be called as a tree. Let us take the example of the graph that we have studied so far. Like this. Now, this is actually a subgraph of the network, but here if you see, the nodes C and D are not connected, so it is not a tree. But if you see this graph, A, B, C and D, here there are no closed loop and all the nodes are connected, so it is a tree. Okay. We can take another example. Here also if you see there is no closed loop, still all the branches, all the nodes are connected by at least one branch. It is also a tree. So you have to connect all the nodes to at least one branch and still make sure that there is no closed loop formed in the process. Like if I connect this path here, then it is not a tree because there is a closed loop. Is it fine? So that is how we define the tree of a network. Now the main challenge lies in determining the number of trees for a graph. Okay? Like we can draw any number of subgraphs, but how many of them will be trees? There are two cases for a complete graph. Complete graph in the sense all the nodes are connected to each other by at least one direct path. For a complete graph, number of trees is equal to, it will be equal to n raised to the power n minus 2 for n greater than 2. But if it is not a complete graph, any general graph, then it is actually determinant of where what is AR? AR is your reduced incidence matrix. We will study further what is the incidence matrix and reduced incidence matrix. So remember these two formulas are independent. You will apply the first formula only when the graph is complete. Okay. Now in any graph how many branches will be there? Branches will be equal to n minus 1. Like as I was showing you examples, here as you can see how many branches we have utilized? 1, 2, 3. And how many nodes were there? There were 4 nodes, we used 3 branches. Because if you increase any branch now, like if you do like this, then also closed loop will be formed. If you use this branch, closed loop. If you use this branch, again a closed loop. So if you increase the branches from n minus 1, there will be a closed loop form in the graph and then it will not be a tree. So in any tree, branches will be always equal to n minus 1. If b is greater than n minus 1, b is the number of branches, then it is not a tree. There will be a closed loop. Okay, like this. Now, what is a co-tree? In a graph, if we remove the tree, then the leftover branches or the set of those branches is known as a co-tree. Like if you see this graph, the complete graph was looking how? A, B, C, like this. Now suppose I remove this tree. A, B, C, D. Then the leftover branches this is known as co-tree. This will be a tree. Okay. So the leftover branches after removing a tree from the graph is known as a co-tree. Okay. Or we can say it is the complement of a tree. If you remove the tree from the sample space of all the branches, then whatever branches are left will be a part of co-tree. The next term we define is known as twigs and links. Twigs are basically branches of tree. And what are links? Links are actually branches of co-tree. Okay. These are also known as cords. So what we do is, in a graph, if we are drawing a tree, then we draw them by a thick line segment and the links will be shown by dotted line segments. Okay, that is how you differentiate between the twigs and the links. Is it fine? So what is a twig? Twig is a branch of a tree and link is a branch of co-tree. As I told you, in a tree how many number of branches are there? N minus 1. So number of twigs will be equal to n minus 1. But there can be any number of links based on the graph. It is not necessary that how many links will be there. But if there are B branches. Then after removing a tree, whatever is left will be links. So how many links will be there in core tree? It will be B minus n minus 1, because twigs plus link will be equal to total number of branches in the tree. Okay. So that is how we draw the twigs and the links. Is it fine? Now let us see a problem. It is asking us to determine the number of possible trees. As you can see here, every node is connected to another node by a direct path. So it is a complete graph. If it is a complete graph, then the number of trees will be equal to n raised to power n minus 2, where n is the number of nodes. So number of nodes here are 4. 4 raised to the power 4 minus 2 is 16. There are 16 possible trees for this network. How those trees are? The first tree, as we can draw, this is my first tree. Second tree, do take care, whatever trees I am drawing, there will be no closed loop, as well as all the nodes will have at least one branch. This is my third tree. This is my fourth tree. Then fifth tree. Then sixth tree. Then seventh tree. Eighth tree. Then ninth tree. Similarly, we can draw the complement of ninth tree, or we can draw like mirror image. This is my 10th tree. Then 11th tree, 12th tree, 13th, 14th, then what is left? This is also done. Then if you see this tree, 15th tree, then the last will be mirror image of this 16th tree. Okay, so that is how we can draw the 16 number of trees for this graph. But do take care that you connect all the nodes and do not form any closed loop. So let us summarize what we covered in this lecture. We first saw what a graph is. Then we learned some terms like path. So basically a path is a traversal from one node to another node without crossing the same node twice. Then we studied about the subgraph. That is a set of branches of a graph. Then we studied about directed graph, in which we gave a reference direction to each branch, and that reference direction does not indicate the direction of flow of current. Then we saw connected graph, in which we can travel from one node to another node by at least one path. Then we saw complete graph, in which there was direct path from each node to every other node. It had NC2 number of branches at least. Then we saw the tree. A tree was a subgraph which has no closed loop and every node is connected to at least one branch. So we saw the number of branches in this. It was equal to n raised power n minus 2 for a complete tree or for a complete graph, and determinant of reduced incidence matrix multiplied by transpose of the reduced incidence matrix for any other graph. Okay. Then we saw twig and link, Twig were the branches of tree and links were the branches of core tree. And what was a core tree? The complementary set of branches of a tree will be known as core tree. Or whatever branches are left in the graph after removing the tree is known as core tree. So how many twigs were there? N minus 1. Links were B minus N plus 1. Okay. So that is what we have learnt in this lecture. In the next lecture we will see what kind of matrices do we define for the case of graph theory. Hi guys, in the last lecture we started with the concept of graph theory. So I told you it is done for the case of more complicated networks so that computer can comprehend those networks and find out the solution of such a network. So in that first we learned the definition of a graph, what is meant by a graph. And then we looked at how to define a path, in which I told you a path is traversal from one node to another without crossing any node twice. Then we looked at the case of directed graph, in which we gave each branch of a graph some direction, some reference direction that does not necessarily represent the direction of current. Then we saw complete and connected graph. In complete graph, there was at least one branch between any two nodes. That is why number of branches were NC2. In connected, there must be at least one path between any two nodes, though it may not be direct. Then we looked at the definition of tree and core tree. I told you a tree is a set of branches which do not form any closed loop, as well as they connect every node to at least one branch. So a tree had n minus 1 branches and a core tree had b minus n plus 1 branches. Then we looked at the concept of twigs and links, in which twigs were branches of a tree and links were branches of the core tree. In this lecture, we will concentrate on the matrices that are defined in the graph theory for the analysis of a network. First such matrix is known as incidence matrix. It gives the relationship between number of nodes, number of branches, and orientation of any branch with respect to any node. So the order of this matrix is n cross b. N is the number of nodes and b is the number of branches. So basically, by looking at this matrix, I can tell what is the direction of any branch with respect to a node. How? The elements of this matrix are defined something like this. It is plus 1 if jth branch goes out of ith node. Like, if there is any branch, suppose this is the first node and this is a branch, it is going outwards, so it will be taken as plus 1. The element corresponding to this will be taken as plus 1. Similarly, it will be taken as minus 1 if jth branch comes into the ith node. Okay, like this. This is my first node. This branch is coming inwards. Okay, so the element corresponding to it will be taken as minus 1. And this element will be taken as 0 if jth branch is not connected to ith node. Suppose this is second node, this is third node, this is b branch. Then the element corresponding to 1 and b, since 1 and b are not connected to each other, will be taken as 0. Okay, so this is how we define the elements of the incidence matrix. Okay, and then let us take an example to define the incidence matrix. Let me take the same graph that we used in the last lecture. It was something like this. let me number the nodes as 1, 2, 3, 4. Now for this we need a directed graph. So let us assume some direction. Let me number the branches as A, B, C, D, E, F. Now when you will form this matrix, you will number the nodes first of all. Then you will number the branches. Okay. Now look at branch A. It is going out of one node, so it will be taken as +1. Then branch B. It is not connected to first node, so 0. Branch C. It is between 2 and 4, not connected to 1, so 0. Branch D. It is going out of first one, +1. Branch E. Between 3 and 4, not connected to 1, 0. Branch F. Going out of 1 towards 3, 1. Okay. The other way to draw this will be like I'll show you in the next row. Branch A. It is between 1 and 2. It is going into the 2, -1. Then branch B. Branch B is connected between 2 and 3. So going out of 2 and into 3. Okay. Branch C. Branch C is between 2 and 4, going out of 2 and into 4. Branch D. Between 1 and 4, so going out of 1 and into 4. Branch E. Between 3 and 4, going out of 3. Let me shift this a little bit towards left. Branch E is going out of 3 and into 4. So for the 3 I will place +1 and for the 4 I will place -1. Branch F going from 1 to 3. So at branch F 1 will be placed at A. Sorry, for branch F 1 will be placed for 1 and -1 for 3. Okay. This way we have covered all the branches. Place zeros everywhere else. Okay. Like this. So that is your incidence matrix. The order of this is nodes cross branches, so it is here 4 cross 6. That is how you can draw the incidence matrix. Now as you can see, whenever there is a branch, it will leave one node and it will enter the other node. That is why sum of a column will be 0. Because a column represents a branch. It will be +1 for the node it leaves and -1 for the node it arrives at. Like this, if you see 1 -1 0, 1 -1 0, 1 -1 0, 1 -1 0, 0 and 0. So sum of the column in any incidence matrix is always 0. Next we come to the reduced incidence matrix. Now when we do the nodal analysis, what we do is we assume node voltages, but to assume node voltages we take one reference node. Okay. Now in reduced incidence matrix we will remove the row corresponding to reference node. Like I'll tell you how. So let us take the same graph that we used in the last matrix. A, B, C, D. The directions that we assumed were like this. So now when you will be forming the incidence matrix, then you will let us consider this, or let us number these as rather 1, 2, 3, 4. 1, 2, 3, 4, and branches will be named as A, B, C, how it were? C, D, E, F. That is, it will be C, D, E, F. Now, when you will be forming the incidence matrix, you will choose one reference node. So, let us choose this node as the reference node. So, how will the matrix look like? We will take only 3 nodes, 1, 2, 3, A, B, C, D, E, F. Then branch A going from 1 to 2. So plus 1, minus 1, 0. Branch B going from 2 to 3, plus 1, minus 1, 0. Branch C 2 to 4, so plus 1, but 4 we are not considering, so place zeros otherwise. D 1 to 4, 1, then 0, then 0. E 3 to 4, 1, then 0, then 0. F from 1 to 3, 1, then minus 1, then 0. Okay. Now in this case, sum of all the rows will be non-zero. Okay. Some of the rows will be 0 in some case and some of the rows will be non-zero in other cases. Where it will be non-zero? Where that branch is incident between a principal node and a reference node. Here 1, 2, 3 will be known as principal nodes and the fourth one will be the reference node. See this? Here if you see the sum, it is 1, 1 and 1 because the branch is incident between a principal node and the reference node. Okay. So what is the order of this matrix? N minus 1 cross B. So here what we have essentially done is we have drawn the incidence matrix and then we have removed the row corresponding to the reference node. Okay. Now we define a term called as isomorphism. What is isomorphism? If incidence matrix of two networks are equal, then those networks are known as isomorphic networks. Okay. That is, their just incidence matrices are equal, so their orientation is same, though the network may be different. Like, if you change the resistance in a network, like one is 2 ohm, one is 4 ohm, graph theory does not care about the value of the elements, but if their arrangement is same, their incidence matrix will be same, both the networks will be called as isomorphic. Let us look at a problem which focuses on the inverse criteria. I have been given the incidence matrix. I have to draw the graph. Now as you can see here, the sum of these rows is non-zero. Sorry, sum of these two column is non-zero and sum of these column is also non-zero. That means it is a reduced incidence matrix. To make it a incidence matrix, we will add one more row corresponding to reference node such that sum of each column is 0. So 1, 0, 0, minus 1, minus 1, 0, 0, 0, minus 1, 0, plus 1, minus 1. Then 0, minus 1, 1, 1, 0, 0. The fourth row that we will add, will try to make the sum 0. Here we will add minus 1, so sum is 0. Here we will add plus 1, 0, 0, 0, plus 1. Now this is my incidence matrix. It consists of 4 nodes. So these are my 4 nodes, 1, 2, 3 and 4. It consists of 6 branches. Let me call it as A, B, C, D, E, F. Now see the A branch. It is incident between 1 and 4. So this is A. See the B branch between 3 and 4. So this is B. Sorry, the direction of B will be from 4 to 3 because at 3 it is minus 1. C branch between 3 to 2. Then D branch between 3 to 1. Then E branch between 2 to 1. This is E. Then F between 4 and 2. Okay, like this. So the direction you have to see that where we have placed plus 1 and minus 1. The branch will originate at the node where we have placed plus 1 sign and it will terminate at the node where there is a minus 1 sign. So this will be the graph of this network. So to draw the graph, you actually need the incidence matrix instead of reduced incidence matrix. So do add one row which is corresponding to the reference node. Next concept we come on to is called as fundamental loop. Now what is a fundamental loop is, I told you when we consider a tree, what happened? There was no closed loop. Okay, and I told you as soon as you add any link to that tree, there will be closed loop. That is known as your fundamental loop. What is a fundamental loop? In a fundamental loop, there is only one link and then rest are twigs. That is, as soon as I add one link, it will become a closed loop. So there will be one link and rest of them will be the tree branches. That is known as your fundamental loop. Let me show you an example. Suppose we take the tree something like this. Okay. Now this is B, E, D. And where are the links? These are my links here. Okay. This is A, then C, then F. Okay. What are the direction of each branch? These are the directions. Now if you see, this is a tree. As soon as I add this F branch, then this becomes a closed loop, and this will be called as fundamental loop, which is your DEF. Okay, that will be your fundamental loop. Now when we want to apply mesh analysis, then we have to assume loop currents. So the direction of loop current that you will assume will be same as the direction of link. That is, I will assume loop current like this. So my fundamental loop 1 is actually DEF, and its direction will be clockwise due to this branch F. Then see this. If we add C, then the loop that will be formed will be BCD. And its direction will be like this. Let me call as I1, I2. If we add this branch A, then the fundamental loop 3 that will be formed will be A, B, E, and the direction of current will be like this, I3. Okay. So you have to assume the direction of current in the direction of the link that you are adding in order to form a closed loop. So how many number of fundamental loops are there? These are same as the number of links. That is, it is same as the B minus N plus 1. That is the number of fundamental loops that you can form. Okay. Like here, how many loops I am forming? 3, because there were 3 links. Out of 6, there were 3 branches and there were 3 links. Let us take another example. Because the tree of a same graph can be various. So let me consider another tree. Like this can be my tree. Then rest will be links. Okay. Now again we have to keep the same directions. Like this. We will number the branches A, B, C, D, E, F. Now first of all, let us add the link D. If we add the link D, what is the fundamental loop that is forming? D, E, F. What will be the direction of current? It will be anti-clockwise. Then fundamental loop 2. Add this branch B. What is the loop that is formed? ABE. Direction of current is clockwise in the direction of B. Now add this branch C. What is the fundamental loop that is formed? It will be A, C, F. Okay. Because it must have only one link and rest of them must be the twigs. So ACF then what is the direction of current? It is clockwise in the current direction of C. So do keep this in mind. Do not form a loop like this, because these two are links actually, and this is also a link. So any fundamental loop consists of only one link and rest of them must be twigs. Okay. So that is how you define the fundamental loop and the loop currents. Now based on this fundamental loop, we define the tie-set matrix. Now what is a tie-set matrix? It gives the relationship between the branch current and the tie-set current. What is a tie-set current? It is a loop current. So it is a matrix that gives the relation between branch current and loop current. So how do we form this matrix? First of all, what will be the order? Order will be loop current or links cross branches, because number of fundamental loop current will be equal to number of fundamental loop, which will be same as the number of links. How many links are there? B minus n plus 1 cross B. This will be the order of the matrix. Okay. Now how to define this matrix? If the branch current aligns with the loop current, then it will be taken as plus 1. If it is opposite to the loop current, it will be taken as minus 1. Just now I told you how to choose the loop current. You will choose the direction of loop current in the same direction as that of link that you are adding. And if the branch current aligns in the same direction, it is good. It is plus 1. If it is in opposite direction, minus 1. If that branch current does not lie in that loop, then it will be 0. Okay. Now let me show you this by means of an example of the tree that we just took. We took the tree like this. Okay. So the direction of branches, this was the branches A, B, C, D, E, F. Now we will take the links here, and links are B, C, D. Branches A, B, C, D, E, F. Now see the branch A. Branch A, when you will keep link B, this will be the loop that will be formed with link B, that is ABE. So the direction of A current lies in the same direction as the loop current. So it is plus 1. Direction of B, obviously it will be in the same direction because we are forming the loop by B. Then C and D are not connected. Direction of E is also in the same direction as the loop current, that is downwards. F is not connected. Then next take the case of C. What is the loop formed? For C it will be ACF, and the direction of current will be clockwise. So direction of A is aligned, B is not connected, C is always 1 because the loop is being formed by C, D not connected, F. If you see F, it is going like this, the loop current, and F current is opposite to the loop current. So it will be minus 1. What about D? When we add D, the current has to be taken anti-clockwise, and the loop that will be formed will be DEF. So ABC are not connected. D will be taken as plus 1 because we have added D. E, it is lying in the same direction, so plus 1. F is lying in the same direction, plus 1. This will be called as your tie-set matrix, represented by M. Okay. That is how we define the tie-set matrix. Is it fine? So its order is equal to number of links cross the number of branches. Now there are certain relations that we define with respect to the branch current or the branch voltage. Okay. Now first of all, the relationship between branch voltages. Now, according to KVL can be written something like this. M into branch voltage must be 0. Now, let me show you this by means of the matrix that we have just derived. Okay, let me write it down. 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, minus 1, 0, 0, 0, 1, 1, 1. And how many branches were there? 6 branches. So branch voltage will be VA, VB, VC, VD, VE, VF. So it will, this is the order 3 cross 6, 6 cross 1. So we will have the order 3 cross 1. So what will be the equation? VA plus VB plus VE. Then VA plus VC minus VF. Then VD plus VE plus VF. This is 0. So actually there were 3 loops that were being formed, and these equations represent the KVL equations in that loops. Okay. That is, we have the 3 equations for KVL. VA plus VB plus VE equal to 0. VA plus VC minus VF equal to 0. VD plus VE plus VF equal to 0. Okay. That is how you can express the KVL in terms of tie set matrix. Similarly, we can express the relationship between the loop current and the branch current. How? We will take the transpose of this matrix. The transpose will be 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, minus 1, 1. And then multiplied by the loop current. The loop current IL1, IL2, IL3. This will give me the branch currents. This is the order is 6 cross 3. This is 3 cross 1. So the result will be 6 cross 1, IL1 plus IL2. Then here we will have IL1, then IL2, IL3, then IL1 plus IL3, and the last element will be IL3 minus IL2. These will be the branch current. Let me show you how. The graph that we took was something like this. The directions were like this. Okay. Now the first loop current that we assumed was due to branch B, and it was like this. So if you see, this is IL1, okay, and the second loop current that we assumed was due to branch C. So it will be like this. So it was like this. Okay, that was the second loop current. And the third loop current that we assumed was due to D. It was like this. Now if you see branch A, in branch A there are 2 loop currents, IL1 and IL2. So it is sum of the both. In branch B, this is A, this is B. In branch B only one loop current, that is IL1. So IL1. Branch C, only one loop current, that is IL2. Branch D, only one loop current, that is IL3. Branch E, this is D. Then which one was E? This is E. It has 2 loop currents, IL1 and IL3. What about branch F? It has 2 loop currents in which IL2 is coming downwards and IL3 is going upwards. So its current will be IL3 minus IL2. Okay. in the same direction as the branch F, because branch F is also upwards. So if we multiply the transpose of the tie set matrix to the loop current, we will get the branch current. If we multiply the tie set matrix to the branch voltages, we will get the KVL equation. That is the significance of your tie set matrix. That KVL equations can be formed by means of tie set matrix. So we can form or we can perform mesh analysis on the network to determine its solution. The next concept comes about the fundamental cut set. First of all, what is a cut set? Cut set is a set of branches which, if cut from the network or which, if cut from the graph, will divide the graph into two parts. How? Let me show you a graph. Okay. This is A, B, C, D, E. Now what you do is, you divide the graph into two parts by cutting the branches C, B and D. If I remove the branches C, B and D, what I will be left with? This branch and this branch. As you can see, the graph is divided into two parts which are not connected to each other. That is how it is known as the cut set. So this set of branch will be known as the cut set, that is CBD. Now what is the difference between cut set and a fundamental cut set? Fundamental cut set is actually a special case of the cut set. In this fundamental cut set, the branches that you are removing, out of that only one branch should be a twig and rest of them should be a link. Like in tie set, I was saying only one should be a link, rest should be twig. Here one should be a twig and rest should be the links. How? For that, first I must know the graph as well as the tree of that network. So let me assume one graph and a tree. Now the graph that I will be assuming will be a complete graph. This is my graph. So direction, let me assume. Okay, this is the same graph that we used in tie set. A, B, C, then D, E, F. Now let me form one tree from this network. Let me call this is my tree. Okay, rest will be links. Now the directions will be like this. Now we have to remove certain branches of this tree so that we can divide the graph into two parts. So let me name the branches here also. A, B, C, D, E, F. Now say if you remove the branches A, B and C. In A, B and C only twig is, B, A and C are links. Then what you will be left with? This node, then this tree. Okay, now you have divided the graph into two parts. That means it will be called as a cut set. Now with every cut set we associate a direction. That direction will be same as the direction of the twig that is connected to that cut set. So here the twig is B. So direction will be like this. Okay, that is radially outwards. Now let us define another cut set. Let me say CDF. Now in this, if you see, only D is the twig, C and F are the links. And after removing this, what I will be left with? This will be the tree and this node will be separated. So we have divided the graph into two parts. Now what will be the direction of this cut set? The direction will be in the direction of D, that is like this. Okay, that is towards left. Then next let us consider this cut set. A, E, F. Okay, here the twig is E, A and F are the links. What will be the direction? in the direction of E, that is downwards. If you do this, this node will be separated from rest of the graph. Okay, so that is how you define the cut set in any graph. Let us take another tree just to clear the concept. So let me define another tree. Okay, it will be like this. The directions will be like this, and rest will be my links. Let me name the branches here also. A, B, C, D, E, F. Now, what you will define? First cut set I will take this. Okay, if I take this cut set, then actually I am taking A, B, C, out of which A is the twig, B and C are the links. Direction will be like this, in the direction of A. Then another cut set I can take C, D, F. Okay, here C and D are the links and F is the twig. The direction in the direction of F, like this. Okay, then the next I can take is this one, BED. In BED, your E is the twig, D and B are the links, and the direction will be downwards in the direction of E. So that is how you define a cut set, in which you will take the direction based on the direction of the twig that you are considering in the cut set. Okay. Now cut set also used in case of one matrix, that is the cut set matrix. It gives the relationship between the branch voltage and the cut set voltage, or we can say branch voltage and node voltage. Because in a tree, every cut set is defined at certain node, so that node voltage will be the cut set voltage. Okay, so it basically expresses the relation between the branch voltage and the node voltage. So, or we can say twig, because every cut set is formed by twig. So what will be the order? Order is actually twigs cross branches, that is n-1 cross B, because number of twigs in any network is n-1. The order of tie set was links cross branches, order of cut set is twigs cross branches. Okay, now how to draw this matrix? In this matrix, the element will be +1 if the twig direction or the direction of cut set is same as the direction of the branch voltage. Okay, and it will be -1 if branch voltage is in opposite direction to the cut set voltage. Or you can just understand, if the branch is oriented in the same direction as the direction of cut set, it will be +1. If branch is oriented in opposite direction, it will be -1. If branch is not at all a part of cut set, then it will be 0. Okay, so let me show you this by an example. Let us take a graph and a corresponding tree. So graph that I am taking is this one. Okay, that is directions A, B, C, D, E. Now let us draw the tree for this graph. The tree you can consider anything. I am considering this one. So it will be A, B, C. Okay, rest of them will be links. Now these are the two links. Now when we are defining, we have to define cut set. Number of cut set will be the same as number of twigs. So let us show direction here also. What will be my first cut set? My first cut set will be this. This is D and E, that is CDE. Direction will be downwards. Okay, so first cut set is CDE. Then the second cut set can be BE. The direction will be inverts in the direction of B. And what can be my third cut set? Third cut set can be A, D and E. Okay. And the direction will be like this. Here A is the twig, D and E are the links. It will also divide the network into two parts. How? This branch will be left and this branch will be left. So it has divided the network into two parts. So my third cut set will be A, D, E. Now when you will draw this matrix, you will take the branches here A, B, C, D, E. Now branch A. The branch A with respect to first cut set, that is CDE. Branch A is not incident on it, so 0. Branch B is also not connected to this cut set, 0. Branch C is actually in the same direction as the cut set, +1. Branch D also in the same direction. Branch E also in the same direction. What about BE? BE is inverts. Branch A is not incident, 0. B is in the same direction, +1. Then C and D are also not incident, E. E is in the opposite direction because the direction of this cut set is inwards. E is coming outwards. Then what about third cut set, ADE? A is in the same direction because anyways it is a twig. The direction of cut set is same as direction of twig, +1. B is not incident, so 0. C is not incident, 0. D is coming outwards whereas the direction is inwards, -1. E is again coming outward, direction is inward, -1. This will be my cut set matrix. Okay. So that is how you define the cut set matrix based on your twigs and the links. Okay. Now as you can see here, if we shuffle this part, then it can be formed into the identity matrix. Here A, B, C are my twigs. That is, the twig part of the cut set matrix is actually identity matrix. Just you have to replace these rows. This you can make the first row. If you interchange first and the third row, basically you will get an identity matrix. So twig part of the cut set matrix is actually identity matrix. Now let us see how we can write the KCL equation by the use of this matrix. Now to write the KCL equation, you will do cut set matrix into branch current should be 0. Let me multiply it with the branch currents here. IA, IB, IC, ID, IE, IF. So what will be the first equation? IC plus ID plus IE equal to 0. As you can see at this node, all the currents are incoming. Sum of all the currents is 0. The next equation, IB minus IE should be 0. As you can see, IB is coming inwards, IE is going outwards. Outgoing current is equal to incoming current. The last, IA minus ID minus IE. As you can see at this node, IA is incoming, ID and IE are outgoing. So that is how we can write this equation. So basically we get the KCL equation by means of this cut set matrix. Is it fine? Now, how to use it in case of branch voltages? This is in case of this is the case for your KCL, but how to use in case of branch voltages? We will say that C transpose into your node voltages will give me branch voltage. Okay. So that is how we can relate the node voltages with the branch voltage for the case of cut set matrix. So that is the use of cut set matrix. The biggest use is the cut set matrix is used to define KCL and the tie set matrix is used to define KVL. Now actually there is a relation between the cut set and tie set. Just now I told you twig part in cut set is actually identity matrix. Similarly, link part in tie set is also identity matrix. So that is why the twig part in cut set matrix is actually negative of the link part in tie set matrix. Sorry, cut set matrix. This is my tie set and this is my cut set. So we can form the two matrices from one another. The twig part of tie set will be negative of the transpose of link part of cut set, and then the link part of tie set will be identity. So we can define one matrix from the other matrix. Okay. So that is how these two matrices are related. If you can determine one, you can determine the other also. So let us summarize what we covered in this lecture. We first saw the case of incidence matrix. There I told you any element is 1 if it is in the direction or it is going outwards, minus 1 if it is coming inwards to a node. Then we saw reduced incidence matrix, in which we removed the reference node row, then the matrix that was left had the order n-1 cross B. Then we saw the case of fundamental tie set. Fundamental tie set was the loop that was formed by addition of a link. So it had all the twigs and one link. So its order based on the matrix that we defined, tie set matrix, was b minus n plus 1 cross b. That is number of links cross branches. Then we saw fundamental cut set. In fundamental cut set, there was only one twig and rest of them were links. Okay. Then we defined cut set matrix, whose order was twigs cross the branches, that is n-1 cross b. And then we saw the relation between the cut set and the tie set, that is m twig is equal to minus c link transpose. And I told you m link is equal to identity and c twig is also equal to identity. Okay. So these are all the concepts that are covered in the graph theory. Out of these, matrices are the most important part. So in the next lecture, we will see some problems that have appeared in GATE examination from these concepts. Hi guys, up to now we have seen the basics of the graph theory, that is, what is the concepts behind the graph theory, what are the terms that are defined like path, like a tree, like a co-tree, and we have also seen the matrices that are defined for graph theory like incidence matrix, cut set matrix and the tie set matrix. In this lecture we will solve some problems that are based on these concepts so that you know how to apply these concepts. Let us get started with our first problem. It is asking us to find the total number of possible trees. Now if you observe here, this branch is missing. Okay. If this branch were present, then it would be a complete graph. Now since this is missing, it is not a complete graph. That is, to find the number of trees, we have to apply this method. Determinant of reduced incidence matrix multiplied by reduced incidence matrix transpose. So for that we need to find the reduced incidence matrix. For that we need a reference node. Let us choose this node as the reference. Then let us determine the reduced incidence matrix 1, 2, 3, and the branches will be A, B, C, D, E. Now the branch A lying between 1 and 2, so it will be 1, minus 1, 0. Branch B 2 and 3, 0, 1, minus 1. Branch C, 3 and 4, 0, 0, 1. Branch D, 2 and 4, 0, 1, 0. Branch E, 1 and 4, that is 0, sorry, minus 1, 0, 0. Because branch E is actually incoming to the node 1. This is my reduced incidence matrix. What is its transpose? Let me write down the transpose here directly. 1, minus 1, 0. Then 0, 1, minus 1. 0, 0, 1. 0, 1, 0. Minus 1, 0, 0. Now if you take the product of these two matrices, first row into first column, it will give me 1. First row into second column, minus 1. First row into third column, it will give me 0. Okay. Then we have to multiply the second row. First row into first column will give me actually 2. Okay. Then second row into first column, minus 1. Second row into second column, it will be 3. Second row into third column, it will be minus 1. Then third row into first column, it will be 0. Third row into second column, it will be minus 1. Third row into third column, it will be 2. Now if we take determinant of this, then it will be 2 into 6 plus, 6 minus 2. Plus 1 minus 1 into 2. 2 into 6 minus 1, it will be 6 minus 1 plus 1 into, it will be minus 2 plus 0, that is equal to 8. So there are 8 number of trees possible for this graph. If you had this branch connected, then it will be a complete graph. Then the number of trees will be 4 raised to power 4 minus 2, that is 16. So just by removing a branch, I have reduced the number of trees to half. Okay. So only 8 trees are possible now. In the next problem, it is asking us to identify which of the following is not a tree for the graph. First one is BCGH. BCGH. It can be a tree because it is connecting all the nodes and it is not forming any closed loop. Okay. Then next, DEFG. DEFG. It is also connecting all the nodes without any closed loop. It is also a tree. ABFG. ABFG. Now this is forming a closed loop. Though it is connecting all the branches, it is forming a closed loop. So this is not a tree. Last is AEGH. AGHE. This is also connecting all the nodes, but it is not forming any closed loop. So this is also a tree. So whenever you are asked to identify which of the following is not a tree, you will check for any closed loops. Okay. So if there are any closed loop, it cannot be a tree, or if it is not connecting all branches, all nodes, then also it won't be a tree. Like if I give you one option like B, D, like this. So B and D are connecting only 1, 2 and 4. 3 and the 5th node are left out. So it is not a tree. In the next problem, it is saying the matrix A given below is the node incidence matrix of a network. The columns correspond to the branches while the rows correspond to the nodes. Now V is equal to V1 to V6 transpose denote the vector of branch voltages, and I126 transpose is branch current. We need to write KVL equation. To write KVL equation, we will multiply it by the branch voltages. That is 1, or let me directly multiply it here. We will multiply it with the branch voltage V1, V2, V3 up to V6. Now what will be the first equation? V1 plus V2 plus V3 equal to 0. Okay. The second equation, minus V2 minus V4 plus V5 equal to 0. Third equation, minus V1 minus V5 minus V6 equal to 0. And the last will be minus V3 plus V4 plus V6 equal to 0. So these will be the KVL equations for this network. Out of this, one equation will be redundant because here we have four loops, or sorry, the four nodes. So actually, and how many branches? 6 branches. So there must be 3 twigs, which is equal to n minus 1, and 3 links. Due to 3 links, we must have only 3 fundamental loops and 3 loop equations, but here we are getting 4 because it is not a reduced incidence matrix. That is why. Okay. So here that means this will give me one redundant equation. So I have to remove one equation in order to get a set of independent loop equations. In the next problem, it is asking us, we have to match list 1 with list 2 in the given figure. So first is 1, 2, 3, 4. 1, 2, 3, 4. If you see 1, 2, 3, 4, there is only one twig and 3 links. Okay. Now if we remove these branches, what is left out? It is left like this. So by removing 1, 2, 3, 4, we have divided the network into two parts. So it is a fundamental cut set, because a fundamental cut set should have only one twig and rest of them should be link. So this is a fundamental cut set. Next is 4, 5, 6, 7. If you see 4, 5, 6, 7, this is the set of twigs. Okay, because it is just a tree. So 4, 5, 6, 7 form a set of twigs. 1, 2, 3, 8. 1, 2, 3, 8. Okay. Now sorry, 1, 2, 3, not 4, just 8. 1, 2, 3, 8. All are a set of links. So it is a set of link. 1, 4, 5, 6, 7. That is 1, 4, 5, 6, 7. It is forming a loop in which only one link is coming, rest of them are twigs. 4, 5, 6, 7 are twigs, one is a link. Now whenever a loop is formed, it is known as a loop, but if there is only one link involved in the loop, then it will be known as fundamental loop. So this is how we will match the option. In the next problem, it is asking for the tree with branches B, D, F. So this is my tree. We need to find the fundamental loops. Okay. Sorry, this is the naming of branches. B, D, F, and then A, E, C. Now if you see, if we connect this branch A, there will be a loop formed A, B, F. Okay. Then if we connect this branch E, then there will be a loop formed D, E, F. If we connect this branch C, then there will be a loop formed B, C, D. Okay, that means this is the correct option. Fundamental loops are those which are formed by one link and rest of them should be twigs. In the next problem, it is asking us the incidence matrix of the graph shown. Now since it is asking us the incidence matrix, we do not need to consider any reference node. That is considered for the reduced incidence matrix. What will be the order? It is node cross branches. So that is 3 cross 3. So I'll mention here the nodes A, B, C. Here the branches 1, 2 and 3. Branch 1 is going from C to A. That is 1 minus 1. Branch 2 going from B to A. That is 1 minus 1 0. Branch 3 going from B to C. Okay, so that will be the incidence matrix. If you consider one node as a reference, remove that particular row. Like if I take C as reference, then what is the reduced incidence matrix? Minus 1, 0, 0, 1, 1. If you see in this matrix, sum of any column is 0. But in case of reduced incidence matrix, sum of these two columns is non-zero. In the next problem, it is asking which of the following statements is incorrect. A tree contains all the vertices of its graph. It is incorrect because a tree contains only the twigs of the graph. Links must be removed that are a part of co-tree. Next, a circuit contains all the vertices of its graph. Actually, a graph is subset of a circuit because we have to remove the sources from the circuit in order to form a graph. That is, graph plus sources is equal to circuit. So obviously the circuit will contain the graph. So this is true. The number of fundamental circuit is same as number of chord. Chord is actually links. As I told you, fundamental loops are those which are formed by one link and rest of them should be twigs. So number of link is equal to number of fundamental loops. This is also correct. There are at least two edges in a circuit. In a circuit, there must be a closed loop in order for the current to flow. For a closed loop, we need at least two edges. So this is also correct. In the next problem, it is saying we have 11 branches, b equal to 11, 6 node, n equal to 6. We need to find independent loops. So what is the number of twigs? It is equal to n minus 1, that is 5. What is the number of links? b minus n minus 1, that is 11 minus 5 equal to 6. Number of links is same as number of fundamental loops. So number of fundamental loops is equal to 6. In the next problem, it is saying we need to consider the graph and tree of the given figure. Tree is given as dotted. So what is the tree? This is actually the tree. 3, 5, 4. Okay, we need to find the fundamental loops. Now if you connect 1, there will be a loop formed 1, 3, 5. So one loop will be 1, 5, 3. Then next if we connect 2, first remove this, now connect 2. Then this is a loop formed 2, 4, 5. Then remove this 2. Next time connect another link, let us say we connect 6. Then there is a loop formed 3, 4, 6. These are the fundamental loops. Why these are fundamental loops? Because these are formed by just one link and rest of them are the twigs. In the last problem, it is asking, we have been given the graph. One possible tree is formed by branches 4, 5, 6, 7. 4, 5, 7, 6. Okay. 6, 7, 4, 5. Now we need to find the one possible fundamental cut set. Okay. Fundamental cut set should have only one branch extra from the twigs. Okay. That is, all should be twigs, one should be the link. If you see 1, 2, 3, 8, these all are links. Okay. So it cannot be a fundamental cut set. Sorry, fundamental. Okay. We are talking about fundamental cut set. In a fundamental cut set, what is the criteria? In fundamental cut set, all should be the links, one should be a twig. So if you see here, there is no twig because twigs are 4, 5, 6, 7. It cannot be a fundamental cut set. What about 1, 2, 5, 6? It consists of 2 twigs. It cannot be a fundamental cut set. 1, 5, 6, 8. Again 2 twigs. It cannot be a fundamental cut set. 1, 2, 3, 7, 8. It has only this as a twig. This can be a fundamental cut set. So if you remove 1, 2, 3, 7, 8 from the graph, you will be left with 6, then 5, 4. We have removed 1, 2, 3, 7, 8. Now if you see, the graph is divided into two parts, hence it is acting as a fundamental cut set. The basic criteria of cut set is removal of these branches should lead to division of graph into two halves, and then a fundamental cut set should have only one twig and rest of them should be linked. So these sort of problems are very common in many PSU exams, and in GATE exams graph theory is kind of irrelevant topic. It is not very much asked. Okay, it is not very frequent. So it is better that you know these concepts, tie set and cut set, because small problems can be asked in other PSU entrance examination. So this is all from the graph theory. Hi guys, up to now whatever networks we have covered, whatever circuits we have seen that power transfers from the source to the load by means of current. Okay, that means for power transfer we need current conduction. Such sort of circuits are known as conductively coupled. Okay, that means power travels by means of conduction. But actually there is another means of power transfer that is known as magnetic coupling. Now what is meant by magnetic coupling? Magnetic coupling means two circuits are not actually connected to each other, but there is some flux linkage between the two circuits, or we can say there is magnetic flux linking the two circuits. Or otherwise you can say that one circuit is producing the magnetic flux which is linking to the other circuit, and hence the power transfer takes place. Or you can understand in this manner, power is generated in electric form which is then converted to magnetic form, okay, which is linking the two circuits, and then again it is converted to electric form. That means for energy transfer or for power transfer there is a magnetic domain between the electrical domains. Those sort of circuits are known as magnetically coupled circuit. Why? Because they are coupled to each other, or they are linked to each other by means of a magnetic domain. Now even when we study about the electromechanical energy conversion, that is when energy is converted from electrical to mechanical form or from mechanical to electrical, there is always a magnetic domain. Okay, that means electrical energy cannot be directly converted to mechanical energy. First it must be converted to magnetic, and then only it can be converted to mechanical. That means these magnetic circuits, or these magnetic domain between the two electrical energy domain or electrical and mechanical energy domain is quite important. Okay. To study the magnetic circuits or magnetic domain, we need to understand the two terms MMF and flux. Like in case of electrical circuit, what happens? We apply some voltage which produces a current. But when we study about the magnetism, now why a magnetic field is produced in the first place? It is produced due to moving charges. And whenever charges are moving at some rate, then there is a current which is equal to dq by dt. That means you can say a magnetic field is always produced due to current. So here the cause will be current. But usually we do not express the cause in terms of current. Rather, here we express the cause in terms of number of turns in the coil into current. So the unit will be ampere turns. This is known as MMF, that is magnetomotive force. Like in electrical circuit, we define EMF, electromotive force. It is the force that generates electrical current. Similarly, MMF is the analog of EMF in the magnetic circuits, and it is responsible for generating the magnetic flux. That means the supply in case of magnetic circuits will be MMF. Okay. Here what is N? Suppose we have a coil which is carrying current I, and it has N number of turns, then MMF will be given by N into I. Next term we define, that is flux. So basically what is the flux? In electrical domain or even magnetic domain, flux is something which is directly related to the number of field lines passing through a unit area. Okay. Number of field lines passing through a unit area. First of all, do remove this misconception that flux is the number of field lines. What I said is, flux is directly proportional to the number of field lines, that is, the more the number of field lines passing through an area. If more number of field lines are passing through an area, like this is the area, if more field lines are passing through it, that means they are crowded, or we can say their intensity is high. Okay. So if more number of field lines are passing through a unit area, then the flux will be higher, or we can say if their intensity is higher, then the flux will be higher. Similarly, so we define magnetic flux as something as a quantity which is directly proportional to the number of magnetic field lines passing through an unit area. That will be your magnetic flux. So usually, in case of electric circuit, the cause is the voltage and effect is the current. In magnetic circuit, the cause is the MMF and effect is the flux. In electrical circuit, current was responsible for transferring the power from one point to another. In magnetic circuits, flux will be responsible for transferring power from one point to another. So these quantities are analog of each other. That is why in most of the circuits we can represent coils and any such magnetic parameters in terms of electrical circuits. So let us see how to relate the electrical parameters with the magnetic parameters. EMF, it gets converted to MMF, which is equal to N into I. Here current, it gets converted into flux. Here we have the Ohm's law, which is V equal to IR. Here Ohm's law converts to Ni is equal to phi into S, where S is my reluctance. Okay. In electrical circuits, we define resistance as rho L by A. In magnetic circuits, S is given by L upon mu A. Okay. Mu is known as permeability. So what is meant by permeability actually? Permeability represents the property of the magnetic material to allow the magnetic field lines to pass through it. Okay. It is like the allowance. The more the magnetic material allows the magnetic field lines to pass, the more will be permeability. Okay. L is the length of the magnetic path. A is the cross-sectional area. Then here we define the electric field intensity E, which is equal to voltage by distance. Here we define the magnetic field intensity, that is H. H will be Ni by L. From where does this arise? This arrives from Ampere's law. Okay. As Ampere's law says that H dot dl is equal to current enclosed, that is Ni. That means H is equal to Ni by L. So that means this relation is valid here also. Here we have current density J equal to sigma E, Here we have magnetic flux density B is equal to mu H. Okay. Then here we have electrical circuits of this form. Like there is a supply, then there is a load. Here we have magnetic circuits like this. There will be an electromagnet on which a coil will be wound, and it will cause a flux through this circuit like this. Okay. Here there will be a current. Here we have laws like KVL, KCL. Here we will have K, MMFL, K, phi L, because voltage will be replaced by MMF and current will be replaced by flux. So Kirchhoff's MMF law, Kirchhoff's flux law. Here we have voltage division rule. Here we will have MMF division rule. Here we have current division in case of parallel circuit. Here there will be flux division in case of parallel magnetic circuit. Okay. So that is how electric and the magnetic circuits are analog of each other. That is why mostly whenever you will encounter a magnetic circuit or a magnetic material, we will represent it in terms of electrical circuit, so that network theorems are applicable and we can easily find the solution. Okay, similar to electrical circuits, like we added resistances in series and parallel, here reluctances can be added in series and parallel. So let us take an example of series magnetic circuit. Now what is meant by series magnetic circuit? It means that flux is constant throughout the entire magnetic domain. Okay. Like if you see here, this is my coil. It produces a flux which flows through the entire material. Remember, just like current needs a closed path, flux also needs a closed path to flow. So it is flowing through the entire material. If it is flowing through the entire material, then flux is same, and hence it is a series circuit. Now as you can see here, we have one material from here up to here of length L1, area A1. Then we have another material of length L2, area A2, and the third material of length L3, area A3. Now, how we will draw the magnetic circuit? First we will draw the cause. The cause will be MMF, which is N into I. Then since all the magnetic materials are connected in series, or you can say since the flux is same, their reluctances will be added in series. And just like current, we will show the flux flowing through the magnetic circuit. This will be S1, S2, S3. What is S1? L1 by mu1 A1. What is S2? L2 by mu2 A2. What is S3? L3 by mu3 A3. Like in series electrical circuit, potential was divided amongst different resistances. Here MMF will be divided among different reluctances. Okay, and flux will be same through each and every reluctance. So what will be the value of MMF1? It will be phi into S1, MMF2 phi into S2, MMF3 phi into S3. So total MMF, which is equal to Ni, is equal to phi S1 plus S2 plus S3. That will be the total value of MMF in case of series magnetic circuit. Now, as you may think, whenever we introduce a air gap, then we are making the circuit discontinuous, then the flux should not exist. But it is not like that. Actually, the air also acts as a dielectric. First of all, what is meant by dielectric? A dielectric means that it has dipoles. Okay, dipoles means a pair of positive and negative charge. That is meant by a dipole where a positive and a negative charge are separated by a certain distance. So air acts as a dielectric as well as a magnetic material. What is meant by magnetic material? It means it can be magnetically polarized. Magnetically polarization means we can induce north pole and south pole in this. So basically, in electrical domain we define the materials as insulators, conductors and semiconductors. Insulators are also known as dielectrics as they have dipoles inside of them which can be polarized, or we can create a dipole by means of electric field. Similarly, in case of magnetic materials, we can create a magnetic dipole by means of magnetic field. Now, as we apply this coil, it will generate an MMF which will be equal to N into I. This will be the cause of a flux, and this flux will magnetize the air. So this flux will also pass through the air. So air acts as a different material altogether with a permeability mu naught, which is 4 pi into 10 raised power minus 7 Henry per meter. Now, if the length of the magnetic material entirely is, let us say, L, then we can say that S magnetic material will be L by mu A. And what about S air? It will be G by mu naught A, where G represents air gap. Now, why is this air gap significant? Usually it is very significant when we talk of the electrical machines, as any basic electrical machine has two parts, a stator and a rotor, which are usually linked by magnetic flux, but between them there is always an air gap. So when we talk about the practical circuits or the practical magnetic circuits, always there will be some air gap because the two circuits will not be in contact with each other. Otherwise, the entire purpose of magnetic coupling is lost. What was the purpose of magnetic coupling? That we do not want the two circuits to be in contact with each other, or we do not want them to be conductively coupled. That is why we want them to be isolated. That is why there must be some air gap between two magnetic circuits. Now both have the same flux, so the total reluctance will be magnetic reluctance plus reluctance of air gap, that is L by mu A plus G by mu naught A. And what about total MMF? It will be equal to flux into total reluctance. Okay. That is how you deal with the magnetic circuit. So if you draw it in the circuit form, it will simply be a series combination of two reluctances with a voltage source equal to MMF. This is your magnetic circuit reluctance. Second will be your air gap reluctance. So next we come to the parallel magnetic circuit. Like in series magnetic circuit, how did I define it? I defined it in a way that the flux must be same across all the magnetic domains. But here we will say that MMF must be same and the flux will get divided amongst different paths. How? A good example of this is shell type transformer. You do not need to understand what is shell type transformer and what are the advantage, disadvantage. We just need to know the magnetic circuit. It will be like this. Now here there will be a winding on the central limb, okay, which carries a current I, and it will produce a flux. This flux will flow through the circuit like this. So if you see, it generates a flux phi which gets divided into phi 1 and phi 2. So we can say that it is an example of parallel magnetic circuit. Now how to draw the magnetic circuit? For that we need to consider different paths of this circuit. Like suppose this path. Suppose this path has length L1. Then this path, this has length L2. Then this path, this has length L3. Now when we will draw the magnetic circuit, we will take a voltage source which is equal to N into I, in series with the reluctance which is equal to S1. Then the flux get divided into two paths, that is S2 and S3. Here S1 is L1 by mu A1, S2 is L2 by mu A2, S3 is L3 by mu A3. As you can see, through this part, the entire flux phi flows, but then it gets divided into phi 1 and phi 2. Okay, so that is called as your parallel magnetic circuit, as two reluctances are connected in parallel. In parallel magnetic circuit, the MMF remains same, but the flux will change. So this is the example of magnetic circuits that we can construct similar to the electrical circuit for any magnetic material. As you might have got it by now, the analysis will be far more simpler as compared to analyzing this type of construction. Now when it comes to the magnetic circuits, as I told you, we will be transferring power from one circuit to another by means of magnetic domain. Now, if you want the energy to be transferred, then in the second circuit, okay, let us call two circuits as independent and dependent circuit. Now, if you want to transfer power, then you have to transfer voltage also, and you have to transfer current also. To transfer voltage and current, the one law that is very important is Faraday's law. The process of transferring the voltage and current from one circuit to another will be called as induction, or you can call it as electromagnetic induction, because due to magnetism, electrical parameters are being induced. Hence, it is known as electromagnetic induction. Now, what is a Faraday's law? It says that whenever a conductor is placed in a variant magnetic field. So here three things are absolutely necessary: conductor, magnetic field, and variation. So if there is a conductor kept in a magnetic field which is variable or which is varying, then there will be EMF induced. Okay, so there is some EMF induced in the circuit. Okay, so how the EMF is induced? As the Faraday stated, EMF will be equal to d psi by dt, where psi is known as flux linkage. Now usually there is a difference between a flux and the flux linkage. The thing is, suppose there is a coil through which a flux phi is passing. Okay, but since it has n turns, every turn of the coil is linked with a flux phi. So the total flux linkage will be n phi. That is how we can calculate the total flux linkage in a magnetic circuit or in a coil. Now, what is meant by variation? We mean to say that this magnetic flux or the magnetic field responsible for this flux must be varying with time in order to generate the EMF. As you can see, this slope must be non-zero for the non-zero EMF. If this slope is 0, it indicates flux linkage is constant. It is not varying with time. But for EMF induction, we need that it should vary with time, due to which this is Faraday's law is defined. Now there was one scientist called as Lenz, which modified this law in order to indicate the direction of induced EMF. He said that EMF is actually equal to minus d psi by dt. This minus sign indicates opposition. Now what does that mean is, induced EMF always opposes the cause of induction. Okay, like let us take a simple example. Any system when disturbed from its original state will try to oppose that change. Like if you are sleeping and if I come to disturb you, you will obviously retaliate. You will obviously want to resist that change. Similar is the case with the magnetic circuits. Whenever we change the flux, an EMF is induced, and that EMF will try to oppose the change of flux. That is, if you are decreasing the flux, this EMF will cause a current to flow, which will try to increase the flux. If you are increasing the flux, this EMF will cause a current which will try to reduce the flux. That is how it will oppose the change. Okay. So that is about your Faraday's law. Okay. So remember, Faraday gave this law, E is equal to d psi by dt, and Lenz modified it by adding a negative sign. Now, what is meant by electromagnetic induction? So whenever a coil produces a flux, okay, and it is time varying, this flux will be linked with another coil, and if it is time variant, then EMF will be induced in the other coil. Okay, so that is how energy is transferred by the process of induction. So first type of induction that we study is known as self-induction. What is meant by self-induction? Now suppose I give you a coil, okay, and we pass a current through it which is a function of time. So the flux that it will generate will also be a function of time. Okay, if it is a function of time, it will cause a EMF. This EMF will oppose this current. So if this EMF is induced in same coil as the original current is passing, then it is known as self-induction. Okay. So now, what is meant by self-inductance? Induction is the process by which EMF will be induced in the same coil which is carrying the current. What is meant by self-inductance? Usually we define that flux is directly proportional to the current that is responsible for it. We provide a proportionality constant as Li, where this L is known as self-inductance. Okay. Or usually we say that psi is equal to Li, which is your flux linkage. That means EMF which was equal to d psi by dt will now be equal to L di by dt, as L is assumed to be constant. Okay. So that is how we can define the self-inductance. Now, to determine the value of self-inductance, we have to understand that is actually L can be understood in terms of psi by I, or we can say n phi by I. Okay. Or we can say n square phi by ni, or we can say n square phi by mmf. Now mmf upon flux will give me reluctance, so n square by s. So inductance is actually number of turns square divided by the reluctance. As I told you, reluctance is given by L upon mu A. What is the value of self-inductance? Mu n square A by L. If the coil is wound in air, that is for a air wound coil, mu is actually equal to mu naught. So inductance will be mu naught n square A by L, where L is the length of the coil, A is the area of cross section, n is the number of turns, mu naught is the permeability of free space, which is 4 pi into 10 raised power minus 7 Henry per meter. Otherwise, for any other material, you will take the relative permeability also. What is meant by relative permeability? It is the permeability of any medium relative to the permeability of free space. So this will be your self-inductance. Okay. Remember, this L is actually the length of the coil and not the length of conductor used to construct the coil. Okay. Since the conductor has multiple turns, obviously the length of the conductor used will be much higher as compared to length of the coil. Okay. Now usually DC as well as AC can be used to generate flux. Flux can be due to DC or AC. But in case of AC, this flux is a function of time. In DC, flux is constant. So that means this electromagnetic induction can happen only in case of AC. Okay. So that is the whole process of the self-inductance. You have to remember the basic formula for the self-inductance that we have used here. So let me summarize what we have covered in this lecture. First, I told you the circuit concept of magnetic coupling, that two circuits are not in actual contact with each other but they have a common flux. Then we studied about electrical versus magnetic circuits, how different quantities are analog of each other. Then we saw different configurations of magnetic circuits like series and parallel circuit. Then we saw the Faraday's law of electromagnetic induction, by which energy conduction or energy transfer can take place. Then we saw how Lenz modified it to make it Lenz's law, minus d psi by dt. Then we defined self-inductance, which came out to be n square by reluctance or mu naught n square A by L for air wound coil, or for any other material mu naught mu r n square A by L. So this is all from this lecture. In the next lecture, we will continue our study of the magnetically coupled circuits. Hi guys, in the last lecture we started with the concept of magnetically coupled circuit. So I told you what are magnetically coupled circuit, in which there is no current flow from the one circuit to another circuit. Rather, there is a flux linkage, that is, a common flux flows through both the circuits in order to induce the EMF and hence cause power transfer between the circuits. So there we saw the concept of magnetic coupling first of all. Then we saw the concept of flux and MMF. So I told you the cause of the magnetic induction is the MMF and the effect is the flux. Then we saw the analogy between electrical and the magnetic circuit, that MMF is analogous to EMF, flux is analogous to the current, reluctance is analogous to the resistance. Then we saw the case of Faraday's law, which is the basic law for electromagnetic induction and states that E is equal to d psi by dt, where psi is the flux linkage. Then we saw Lenz's law, which added a negative sign before this in order to show that induced EMF opposes the cause of induction. And the last that we saw was the case of self-inductance. Okay, so that is all what we covered in the last lecture. We also derived an expression for self-inductance, that is mu naught n square A by L, where n is the number of turns, A is the cross-sectional area and L is the length. The next concept that we are going to study is the mutual inductance. Now what is meant by mutual inductance? Self-inductance, what does that mean? When you pass a current through a coil and the EMF is induced in the same coil, it is known as self-induction. Similarly, mutual induction is the process in which we pass current through one coil and EMF gets induced in the neighboring coil. As you can see here, we have two coils. I1 passes through one coil, but EMF is shown across the second coil. Now whenever current passes through a coil, it generates flux. Let us say I1 will cause MMF1, which will cause Phi1. Now when this flux is produced in a coil, some of it will link the other coil and other will be lost in the air. So this flux has two components, Phi L1 plus Phi 12. What is Phi L1? It is known as leakage flux. So what is the definition of leakage flux? It is the flux that links only one of the two windings and not both. Okay, that means this flux is linking the first winding, but does not link the second winding, rather it is lost in the air or it is leaking. Okay, due to which phi 1 2, which is the mutual flux, is always less than phi 1. So we express it as a fraction of phi 1, that is k phi 1, where k will belong to 0 to 1. Okay, it can take all the values between 0 and 1. Now phi 1 2 represent the flux due to 1 linking in 2. So first subscript represent the cause of flux, second represent in which coil it is linking. Okay, due to 1 linking in 2. That is the representation phi 1 2. Now if this is the flux, then what is the flux linkage in the coil 2? The flux linkage in coil 2 will be number of turns into the flux. So what is the EMF induced? D psi 1 2 by dt. I am not showing negative sign because I am interested in magnitude. That is N2 d phi 1 2 by dt, because number of turns is not a function of time, so we can take it out of the derivative. Now as we defined in case of self inductance, phi is equal to Li1. Here we will define phi 1 2 is M12 into I1. M12 is mutual inductance of 2 due to 1. Okay, so that means I can say that phi 1 2 is M12 I1. That means, sorry, we will call it psi 1 2. Psi 1 2 is N12 I1. Then what is EMF into d psi 1 2 by dt, that is M12 di1 by dt. That is the flux induced, the EMF induced due to the mutual induction. Okay, it is directly proportional to the derivative of the current and multiplied by the mutual inductance. Now let us try to derive an expression for this mutual inductance. Now the magnetic flux density produced by current in coil 1 is actually mu naught N1 I1. This expression has been derived by Ampere's law. It can be written as mu 1 N1 I1 by L. This N1 is actually small n1 or lowercase n1 is actually number of turns per unit length. That is why I am writing total number of turns upon length. Now what is the flux? Flux is equal to B1 into A. That is mu naught N1A I1 by L. Now what is phi 1 2? It is K phi 1 mu naught N1A K I1 by L. Now what is psi 1 2? It is N2 into phi 1 2. That is mu naught N1 N2 A by L K I1. Then what is M12? M12 is actually psi 1 2 by I1. So it comes out to be mu naught N1 N2 A by L into K. Okay, this is your mutual inductance of 2 due to 1. If you wish to derive a similar expression for M21, that is mutual inductance of 1 due to 2, then you will have to consider the initial current in coil 2. So B2 will be equal to mu naught N2 I2, or we can say mu naught N2 I2 by L. Then what will be phi 2? Phi 2 will be actually mu naught N2 A by L into I2. Then what is phi 21? Mu naught N2 A by L K I2. Now why I am considering K as same? Because the leakage flux is due to the distance between the two coils. And since the distance from 1 to 2 will be same as distance from 2 to 1, the amount of leakage flux will also be same. Okay. Now what is psi21? Mu naught N1 N2 A by L Ki2, or we can say N1 into phi 21. Now what is M21? Mu naught N1 N2 A by L into K, which is equal to psi21 by I2. So it is same as M12. That is, mutual inductance remains the same whether you determine it from 1 to 2 or from 2 to 1. That means I can directly say that M12 equal to M21 equal to M. Now what is the value of M12? It is equal to psi12 by I1. Psi12 is actually N2 phi12. That is N2 K phi1 by I1. What is the value of M21? Psi21 by I2. That is N2 phi21 by I2, or N1 K phi2 by I2. Now if you multiply both equations, we will get M square is equal to N1 phi1 by I1 N2 phi2 by I2 into K square. That is K square L1 L2. So what is the value of K? M by under root L1 L2. This is known as coefficient of coupling. Okay. It indicates how well the two coils are coupled, because it is also equal to phi12 by phi1. If the coils are perfectly coupled, then there will be no leakage flux and the entire flux will serve as the mutual flux. So the coefficient of coupling for the perfect coupling will be 1. Okay. That is the physical significance of this coefficient of coupling. Is it fine? So this is how you determine the mutual inductance, and remember, mutual inductance remains the same on both the sides. Okay. So if K is equal to 1, it is your ideal coupling, or it is called as critical coupling. But usually there will be some leakage flux. So practically we will say that K is less than 1. K greater than 1 is impossible, because the linkage flux cannot be greater than the total flux. Total flux will always be higher. Now let us try to determine the energy stored in a system of coils. If you want to determine the energy, energy can be in two forms. One due to self-inductance, other due to mutual inductance. Now how to determine the energy? It is integral of power. Power is integral of Vi. So first let us determine due to self-inductance. Due to self-inductance, voltage induced is equal to, let us say, L1 di1 by dt. So what is energy of 1? Integral L1 di1 by dt into dt into I1. Okay, because power is equal to Vi. So L1 can be taken out common. It can be written as I1 di1. Now integration of I1 with respect to I1 will be I1 square by 2. So half L1 I1 square. Similarly, energy of 2 due to self-inductance will be half L2 I2 square. What about the energy due to mutual inductance? Now due to mutual inductance, EMF in second coil is equal to M di1 by dt, because EMF in 2 is due to current in 1. So what is power? E2 I2, that is M I2 di1 by dt. So what is energy? Or we can say energy due to mutual inductance will be integral M I2 di1 by dt into dt. So M into I2 can be taken out common. It will be di1 that is M I1 I2. Now by this concept I can say that the total energy stored will be half L1 I1 square half L2 I2 square plus minus M I1 I2. Why can I use a minus sign? Because energies must get added up. Because if EMF induced is negative, then power will be negative, then energy will also be negative. So if you use a negative sign, it is known as negative coupling. Okay. Or we can say subtractive coupling. In this case, what happens is that both the inductors will try to reduce the flux of each other. Or you can say their flux will be mutually opposing. In that case, you have to use a negative sign. You can also understand in this term the EMF induced due to self-inductance will be opposite to the EMF induced due to mutual inductance. In that case, you will have to use a negative sign in case of mutual energy. Is it fine? So, opposing flux, you have to use negative sign, and adding flux, you have to use positive sign. That is, if both the flux are getting added up, you will use a positive sign. Let me show you this by an example. How can this happen? This will happen. Suppose there are two coils. Let me first draw a structure. Then suppose this is current I2, I1. Now by right hand thumb rule, what will be the direction of flux? This. And by right hand thumb rule, the direction of flux will be like this. So as you can see, this flux will flow like this, clockwise. The other one is also clockwise. So they are getting added up, which means it is adding flux. Now if you reverse the direction of I2, that is if you take it outside, then by right hand thumb rule, the direction of this flux will also be upwards. That is, one is clockwise, other is anti-clockwise. Then this is opposing fluxes. So actually, in case of transformer, one current is into and other current is out of the coil, due to which both the fluxes are opposing. That is the basic principle of transformer, that the primary flux will oppose the secondary flux, or the secondary flux will oppose the primary flux. Okay. That is why there we have a opposing polarity. There you have to use a negative sign in the energy. Next, let us understand the dot convention, which is generally used to represent the magnetically coupled circuit. Now first of all, the first thing that you must understand, wherever you have a dot, you will place a positive sign like this. Doesn't matter whether the EMF induced is positive or negative, the convention or the representation, or you can say the positive terminal, will be the one which has a dot sign. Okay. Now it may so happen that the EMF is minus 10 volt, which means the assumed terminals are incorrect. You have to reverse the sign of the terminals. I'm not saying once you have assumed EMF will be like that. EMF may be positive as well as negative. So EMF can have opposite polarity also. Okay. But you will assume plus minus based on the dot. Now, suppose we take the first case. Now what happens is, you have to consider the case where current enters dot. Okay, here this current is entering the dot. In that case, dotted terminal is positive on the other side. Like on the other side, it will be happening like this. M di1 by dt. You will induce a voltage source like this. Okay, that is dotted terminal will be marked positive. Is it fine? Other terminal will be taken as negative. What happens when the current leaves the dot? If you see here, this is I2. I2 is leaving the dot. Then the positive terminal or the dotted terminal will be negative. You can say that the dotted terminal will be negative on the other side. Negative if current leaves the dot. So how will the circuit on the first coil look like? Since current is leaving the dot, you will have to use a negative sign. So it will be like this. This dotted terminal is negative because dot was at the bottom. So it is taken as negative. So plus minus sign will be like this only. Is it fine? So that is how we induce the EMF in the coil based on the dot convention. Remember, current entering the dot, other dotted terminal will be positive. Current leaving the dot, other dotted terminal will be negative. Let me show you this by another example. Take this case. Here current is flowing like this. So first let me ask you whether the current is entering or leaving. It is entering. Now since it is entering the dot, what will happen is here the dotted terminal will be positive. So if dotted terminal is positive, how it will look like? It will look like this. This dotted terminal will be positive, so it must be like this because the bottom terminal is dotted. But we have shown E1 like this. But as you can see, we are getting opposite polarity, so we will say E1 is equal to minus M di2 by dt. Okay, because the assumed polarity is opposite to what it should be. In this case, if you see, current is flowing like this, so it is leaving dot. If it is leaving dot, it means if it is leaving the dot, that means the dotted terminal on the other end will be negative. Okay, if the dotted terminal on the other end is negative, then how will you show the EMF source? The EMF source here will be like this. Okay, the dotted terminal or the bottom terminal is negative. But we have shown E2 like this. So the polarity that is assumed is opposite to the actual polarity. So E2 will be minus M di1 by dt. Okay, so we have to use a negative sign in the expression. So remember, if the assumed direction is same as the actual direction, no need of negative sign in the expression. If assumed and the actual direction are opposite, you have to use a negative sign in the expression. That is how the dot convention works. Now based on that, the equivalent inductance of coils connected in series or parallel will change. How? First let us connect the coils in series. Now if you see here, this is dot, this is dot. This is known as positive coupling. As the current is entering both the dots. So since the current is entering the dot, what I'll assume? That the other dotted terminal will have positive EMF. So the circuit will be plus minus M di2 by dt, then plus minus L1 di1 by dt. Then for the second coil, dotted terminal will be positive, M di1 by dt, then L2 di2 by dt. So we have shown both the EMFs due to self as well as mutual inductance. So now this is the total voltage across coil 1, across coil 2. So what is V1? M di2 by dt plus L di1 by dt. Now since they are in series, I1 and I2 are same, so it is M plus L di by dt. What about V2? V2 is M di1 by dt plus L2 di2 by dt. Again, since both are same, M plus L di by dt. Now the total voltage will be V1 plus V2, that is L2, L1, L2 here, L1 plus L2 plus 2M di by dt. So what is the equivalent inductance? L1 plus L2 plus 2M. If the coils are connected in series and they are positively coupled or they are additively coupled. Now if we see the another case, now here if you see the dots are on the opposite ends. Okay, so current is entering this dot, that means the dotted terminal will be positive, so this terminal will be positive. Now current is leaving this dot, so the dotted terminal will be negative. How will the circuit look like? Negative positive M di2 by dt. Then inductor positive negative L1 di1 by dt. Then again inductor positive negative L2 di2 by dt. Then negative positive M di1 by dt. Now what is the voltage across V1? V1 is equal to L1 di1 by dt minus M di2 by dt. Again, since both currents are equal, L1 minus M di by dt. What about V2? It is L2 di2 by dt minus M di1 by dt. That is the voltage across coil 2. So it is L2 minus M di by dt because both currents are same. Again we will add V equal to V1 plus V2, which will result in L1 plus L2 minus 2M di by dt. So what is equivalent inductance? L1 plus L2 minus 2M. Here L1 plus L2 plus 2M. So you have to use plus sign if both the dots are on the same side. You have to use minus sign if the dots are on the opposite side of the coil. Similarly, we can derive the case for the parallelly connected coils. If the dots are on the same side, current will be entering both the dots. So here equivalent inductance will come out to be L1 L2 minus M square by L1 plus L2 minus 2M. Okay. If the dots are on the opposite side, EMFs will be like this, negative positive, and here it will be negative positive, like this. EMFs will be induced in the opposite polarity. So here equivalent inductance will be L1 L2 minus M square over L1 plus L2 plus 2M. Okay. So that is how the equivalent inductance will look like for the case of parallelly connected coil. So the important thing here is you understand that how to induce the EMF or what polarity of EMF you should need to consider. Okay. So based on whether the fluxes are aiding each other or they are opposing each other, you have to assume the direction of induced EMF. Next, if we represent the transformer in form of a T circuit, what happens is, suppose there is a mutual inductance M and the self inductance L1 and L2. This is the case of a transformer with turns ratio N1 is to N2. This current should be I2. Now, what is the EMF induced in 1? It will be L1 di1 by dt. Current is entering both the dots, so dotted terminal will be positive, plus M di2 by dt. Okay. Now if you see here in the T circuit we have written L1 minus M, M, L2 minus M. Why? Because this can be written as L1 minus M di1 by dt plus M d by dt of I1 plus I2. Okay. That means I have added and subtracted this term M di1 by dt. Similarly, what about E2? E2 is L2 di2 by dt. Since current is entering both the dotted terminal, mutually induced EMF will add this M di1 by dt. So how will this look like? L2 minus M di2 by dt. We have subtracted the term M di2 by dt. So we have to add this too. I1 plus I2. Now since the total current I1 plus I2 is passing through M, it will be shown as shunt branch in the T circuit. And these branches will be L1 minus M and L2 minus M. So that is how we represent a T equivalent circuit of a transformer. Okay. Similarly, if the coils had dots on the opposite side. Now if you see current is entering this dot, so this dot will be positive. But current is leaving this dot, so this dot will be negative. So how will the EMF be induced? This dot is negative, positive, then plus minus. Here how will the EMF be induced? Plus minus, minus plus. Okay. So what is the EMF E1? It is L1 di1 by dt, but mutual is opposite, M di2 by dt. Similarly, what is E2? L2 di2 by dt minus M di1 by dt. Now we have to make it I1 plus I2. That is, we have to add and subtract the term M di2 by dt. So L2 plus M di2 by dt minus M d by dt of I1 plus I2. Similarly here, L1 plus M di1 by dt minus M d by dt of I1 plus I2. So that is how minus M, L1 plus M and L2 plus M. So that is how you represent a transformer in the form of a T circuit. So let me summarize what we have covered in this lecture. We first saw the concept of mutual inductance, which I told you is same from both the sides. We derived an expression like mu naught N1 N2 K A by L, where K is the coefficient of coupling, which is M under root L1 L2 less than 1. Ideally, K is equal to 1. It is actually the ratio of mutual flux linkage by total flux. Then we saw the concept of, after mutual inductance, then we saw the concept of dot convention. And there I told you, if current enters the dot, then the other dotted terminal will be positive. If current leaves the dot, other dotted terminal will be negative. Then we derived energy due to coils. We saw that for negative coupling or for opposing fluxes, we must use negative sign with mutual energy, and with adding fluxes, we must use positive sign. After that, we saw the case of series and parallel connection of coil. And last, we saw the case of T circuit of transformer. Okay. So these are the important concepts in your mutually coupled circuits. Okay. Though the question is very rare, but these concepts are very generic and very important. Hi guys, in the last few lectures we have focused on the concept of magnetically coupled circuit, in which we saw the power transfer happens by the process of electromagnetic induction. And actually the two circuits are not connected to each other, rather their magnetic field will be responsible for transferring the power. So in this lecture what we will do is, we will see a few problems based on magnetic circuits and the magnetically coupled circuit. Okay. So, if we see the first problem, it is asking us to find the equivalent inductance. Now, when we are finding the equivalent inductance, in addition to the self-inductance, we have to take care about the mutual inductance. And for taking care of mutual inductance, we need to understand whether the coils are positively coupled or negatively coupled. Or we can say whether their fluxes are additive or they are opposing each other. Now, to determine the direction of flux, we usually use a right-hand rule. Now, if the current is flowing like this, then if you curl your fingers in the direction of current, then the direction of thumb will point to the direction of flux like this. And if the current is flowing like this, then it is flowing anti-clockwise, direction of thumb will be upwards. Okay, like this. So that means we have to find the direction of flux by means of right hand thumb rule. For coil number 1, if you curl your fingers in the direction of current, the direction of flux 1 is towards left. What about coil number 2? In coil number 2, if you curl your fingers in the direction of current, the flux is oriented towards right. What about coil number 3? Again, left. Okay. So coil 1 and 3 are positively coupled. 1 and 2 are negative. 2 and 3 are negative as their fluxes are opposing each other, whereas 1 and 3 are positive. So what will be the equivalent inductance? Self-inductance will directly be added up because they are in series. But what about mutual? If for 1 and 2, since negative coupling is there, minus 2m 1 2. 2 and 3 negative is there, 2m 2 3. But for 1 and 3 positive is there, 2m 1 3. That is 6 plus 5 plus 4 minus 2 into 2, 2 into 1 plus 2 into 3. That is 15 Henry. Okay. So that is how you need to determine the equivalent inductance based on the mutual inductance. In the next problem, it is asking us to find the equivalent inductance across x and y. Again, we have to determine the direction of flux for coil x. Where is the direction of flux? It is upwards. Okay. And if it is upwards, actually, it will flow like this. That is clockwise. What about coil y? If you see towards coil y, it is towards left. If it is towards left, that means anti-clockwise. What about coil? Sorry, let me number these. This is not x and y. This is coil number 1. This is coil number 4. Now look at the coil number 3. For coil number 3, the flux is downward. For downwards, it means clockwise because it will flow like this. For coil number 2, the flux is actually towards left. Left in this case will mean it is towards left, that means clockwise. So 3 fluxes are clockwise and 1 is anti-clockwise. So what is the equivalent inductance? Self-inductance will directly get added up. What about mutual? 1 and 2 are positively coupled as their fluxes is same in the same direction. 2m 1 2. What about 1 and 3? For 1 and 3, they are also positively coupled, 2m 1 3. What about 1 and 4? Oppositely coupled, minus 2m 1 4. What about 2 and 3? In the same direction, 2m 2 3. What about 2 and 4? Oppositely coupled, 2m 2 4. What about 3 and 4? Opposite, 2m 3 4. This way, for the 4 coils, we will have 6 combinations. Okay, these 6 values are given here. So what will be the equivalent inductance? 5 into 4 plus 2 into, if we take the positive terms, M12 that is 2, M13 that is 1, plus M23 that is 2. These are the positive terms minus negative terms. M14 is 1. Then M24 is also 1. Then M34 that is 2. Okay, that is 20 plus 5 into 2, 10 minus 8. So it is 22 millihenry. Okay, so that is how you always need to first of all identify the direction of flux Based on that, you define which coils are positively coupled and which are negatively coupled. And after determining that, then you will allow or you will put the mutual inductance with a positive or a negative sign. For positive coupling, you will use a positive sign. For negative coupling, use a negative sign. In the next problem, it is asking us to find the output voltage. Now, V0 is actually the potential difference between voltage of L1 and voltage of L2. That is V1 minus V2 equal to V0. Now, voltage at this point is actually Vs. Okay. As both are in parallel. We have to find the voltage across inductor 2. Now, as you can see here, it is open circuited, so current is 0. That means in coil 1 there will be no mutual induction. That means Vs will be equal to L1 di1 by dt, or I can say di1 by dt is equal to Vs by L1. There is no mutual inductance term because I2 is 0. Now, since the current is entering the dot in L1, this terminal will be positive, this will be negative. I told you whenever the current enters the dot, the other dotted terminal will be positive. Okay. So what is the voltage across L2? It is M di1 by dt. There is no self-induction term because I2 is 0. Or you can write down like this, L2 di2 by dt, which again will be equal to M di1 by dt. Is it fine? Because I2 is 0. Now, if you substitute di1 by dt, it will become M Vs by L1. Okay. So, to find out V0, what we will say, Vs 1 minus M by L1. Because it will be Vs minus Vs M by L1. Is it fine? So, that is how you need to take care in case of these type of problems, which side is open circuited, and then equate that side current to be 0. In our next problem, again it is asking us to find the equivalent inductance. Now, in such a complicated problem where all the three coils have some coefficient and they are not a series or a parallel connection, then what we have to do is, we have to assume a voltage source here, V, and a current I. Now, V is equal to L equivalent di by dt. So, what we have to find L equivalent is V upon di by dt. Okay. Now, if I is going here, I will assume it is I1 is here and I minus I1 is here. Now, if you see, current is entering the dots in both L1 and L2. So, L1, L2, they are positively coupled. Current is entering L1, leaving L3. So, L1, L3, they are negatively coupled. And then L2, L3, entering L2, leaving L3. So, L2, L3 are also negatively coupled. Now, based on this, if I apply KVL in terms of V, L1 and L2, then V will be equal to L1, the current through is di by dt, plus L2, current is di1 by dt. Now, we have to consider the terms containing mutual inductance. With L1, we will take a positive sign, M12 di1 by dt, because current in L2 is I1. Now, with about M3 or M13, about M13, we will take a negative sign because 1 and 3 are negatively coupled. So, what will be there? Minus M13 d by dt of I minus I1. Then next we have to consider about coil number 2. For coil number 2, with 1 we will take a positive sign, M21 di by dt. With 3, since 2 and 3 are negatively coupled, we will take a negative sign, M23, then d by dt of I minus I1. Now, if we collect the terms containing di by dt, it will be L1 minus M13 plus M21, then minus M23. Okay, plus di1 by dt terms containing I1, L2, M12 plus M13 plus M23. Now what is the coefficient of di by dt? L1 is 10 minus M13 2, that is 8, plus M21 1, that is 9, minus 3 6. Okay, so this comes out to be 6. What about this? 10 plus 1 11 plus 2 13 plus 3 16. So it will give me a equation that is V is equal to 6 di by dt plus 16 di1 by dt. Now let us apply KVL in terms of V, L1 and L3. Now V will be equal to L1 di by dt plus L3 d by dt of I minus I1. Now we have to consider mutual inductance in case of L1. It will be with respect to 2 as well as with respect to 3. With respect to 2 it will be positive, but with respect to 3 it will be negative because both are negatively coupled. Now we have to consider mutual inductance for 3. With respect to 1 it will be negative, but with respect to 2 it will be also negative. Now we have to consider the coefficient of di by dt. It is L1 plus L3 minus M13 minus M31, okay, plus di1 by dt. It will be minus L3, then plus M12, then plus M13 minus M32. Okay. Now if we find the coefficient of di by dt, it is 10 plus 10 20, 20 minus 4 it is 16. Okay, that means 16 di by dt. What about di1 by dt? Minus L3 minus 10 plus M12 it is minus 9 plus M13 minus 7 minus 3 is minus 10. So that is how we have got the two equations in terms of I and I1. If I have got two equations in terms of I and I1, we have to eliminate I1 because we need di by dt. Okay. So if you want to eliminate I1, here this will also be V. Subtract both these equations. If we subtract minus 10 di by dt plus 26 di1 by dt, it is equal to 0. That is di by dt is equal to 2.6 di1 by dt. Substitute in the first equation. We can substitute the value of di1 by dt. Then we will get L equivalent is equal to V upon di by dt. That comes out to be 12.15 Henry. You have to substitute the value of di1 by dt, that is di by dt upon 2.6. Okay. In the next problem, it is asking us to find the resonance frequency. Okay. The resonance frequency is actually 1 by 2 pi under root LC. So here we will take L equivalent. Now both these coils are connected in series, but their dots are on opposite side. So what is L equivalent? L1 plus L2 minus 2M. That is 2 plus 2 minus 2. That is 2 Henry. So what is frequency? 1 by 2 pi under root 2 into 2. That is 1 by 4 pi Hertz. Okay. So that will be your resonance frequency for this case. Okay. So here also you have to take care, whenever you are finding the resonance frequency, you have to consider the equivalent inductance instead of just the self inductance. Is it fine? In our next problem, it is asking for series resonance, what should be the coefficient of coupling. Now we know for resonance, XL must be equal to XC. That means XL here in this case must be equal to 12 ohm. But as you can see, the sum of the self inductances, or we can say X11 plus X22 is actually 10 ohm, but we need 12 ohm. That means these must be positively coupled. Okay, because if these are negatively coupled, then the overall inductance will reduce. But here we have to increase the inductance, so there must be positive coupling. So what is the overall inductance actually? L1 plus L2 plus 2M. In terms of reactance, X equivalent will be X1 plus X2 plus 2XM. That means it is equal to 10 plus 2XM, which is equal to 12. So XM should be 1 ohm. That means if you want to find the coefficient of coupling, it is M upon under root L1 L2. It can be written as XM upon under root X1 X2. We have just multiplied and divided both the terms by omega. That means it is equal to 1 by under root X1 X2 is how much? 2 into 8. That is 1 by 4, or we can say 0.25. So the coefficient of coupling in this case will be 0.25. Is it fine? So whatever formulas we have learnt in terms of inductances, the same can be applied in case of reactances. Okay, that is, just we have to multiply the term by the omega. What I mean to say is, coefficient of coupling is M upon under root L1 L2. It should be also equal to omega M by omega under root L1 L2. That is XM by under root X1 X2. Because if you take omega inside the root, it will become omega square. That is omega L1 into omega L2. In the next problem, it is asking us to calculate the phasor currents. But here we have been given mutual inductance as well as self. But if you see, current is entering one dot and it is leaving the other dot. That is, they are negative coupled. So mutual inductance term shall be taken as negative. So if we apply KVL, then 12 minus J4, or minus 2 plus it is 12. Then plus 2 minus it is minus J4 into I1. Then plus 2 minus it is minus J5 into I1. Then what about the mutual term? Mutual term will be taken with a plus sign because it will be like minus plus. Then plus J. What is the mutual inductance? 3. J3 I2. Okay. What I mean to say is, if plus minus are like this, mutual inductance will be opposite, that is minus plus. That is 12 equal to how much? J5 minus J4 I1 minus J3 I2. That is J1 Ji1 minus J3 I2 is equal to 12. This is our first equation. Now let us apply KVL in the second equation. How will be the plus minus sign? Based on the current direction, plus minus, then it will be plus minus, because the dotted terminal will be negative. Okay, so the dotted terminal will be negative, it will be minus plus. Okay, dotted terminal must be negative. See, actually in the primary, current is entering the dot. So here dotted terminal must be positive. It must be like this. Okay. Since the current in primary enters the dot, so in the secondary, the dotted terminal will be positive. In the secondary, the current leaves the dotted terminal. So in primary, the dotted terminal will be negative. That is why we took the sign as minus plus in the primary. Okay. Now if we apply KVL, from plus to minus it will be minus 12 I2. In J6 again we are going from plus to minus J6 I2. But in case of mutual we are going plus to minus to plus, that is plus J3 I1. This must be 0. It implies J3 I1 minus I2 12 plus J6 must come out to be 0. So we have got two equations in I1 and I2. If we solve these two equations, we get the solution as I1 will be equal to 13.01 angle minus 49.39 degree ampere and I2 equal to 2.91 angle 14.04 degree ampere. Okay, so just remember this universal rule. Let me tell you this again. If the current enters the dot on one side, on the other side the dotted terminal is positive. That is why this will be plus minus, because current is entering the dot here. Now here the current is leaving the dot. So that is why here the dotted terminal will be negative. So EMF will be minus plus. That is how you have to induce the EMF. In our last problem, it is asking us to find the T equivalent of the transformer. In the T equivalent, this is actually equal to L1 minus M, since both are positively coupled. L1 minus M means 10 minus 2, that is 8. This is L2 minus M, that is 4 minus 2, that is 2. And this is actually equal to M, so this is 2. So that will be the T equivalent of the transformer. Okay. So that is, these kind of problems can be framed from this topic, but the most common type of problems are based on resonance along with the mutual inductance. So be clear about those problems very well. Otherwise the equivalent inductance can be asked, but not more than that. Okay. So this is all about your mutually coupled circuits. Hi guys, up to now whenever we talked about the AC circuits, we were talking about a voltage of the form V is equal to Vm sin omega t plus phi, where Vm was the amplitude and phi was the phase. Such sort of voltage is known as single phase AC. Why single phase? Because it has a single value of phase, that is phi. Now whenever multiple such voltages having the same frequency but different phases are present in a system, it is known as polyphase AC. Like if we talk about two phase, here there is a phase shift of 90 degree. So there will be two voltages, V1 is equal to Vm sin omega t plus phi 1, V2 is equal to Vm sin omega t plus phi 1 minus 90. This way we have two voltages which are having the same phase, which are having the same frequency, but phase shift is 90 degrees. Okay. So for two phase shift is defined to be 90 degree. For phase greater than 2, shift should be 360 by n. Okay. Like for three phase, what should be the phase shift? 120 degree. 360 by 3, that is 120 degrees. Okay. That is the concept of the polyphase AC circuits. So the single definition of polyphase is whenever we have multiple AC voltages operating at the same frequency but different phase angles. Now in a generator, how to generate polyphase voltages? What we do is, whatever shift we need, that is 360 by n, we will keep the coils separated by this angle in space. Like as you can see here the coils have been separated by each other by 120 degrees, due to which whenever the rotor will rotate, it will first lie along A, then maximum voltage will be in A. Then after rotating by 120 degree, it will lie along B. Maximum will be in B. Then again after 120, it will lie along C. This way, there will be a phase shift in ABC voltages of 120 degrees. Okay. If you want 90 degree phase shift, you will keep the coils at 90 degree with respect to each other. That means whatever is the phase shift needed in a generator is actually the space displacement. Space displacement of coil in machine. Okay. Whatever generator you are using to generate the voltages, keep the coils separated by 360 upon n in order to provide a phase shift of the same value. Okay. So in this chapter, we will mostly focus our attention on the three-phase systems, as that is the most prominently used multi-phase system or the polyphase system. Now whenever we want to represent multiple voltages having the same magnitude, having the same frequency but different phases, then we make use of the phase shift operator. Now whenever I give you a complex number, let us say Z equal to R e raised power j theta. If it is multiplied by a quantity j phi, then what happens? R e raised power j theta plus phi. That is, if the complex number was earlier like this, magnitude R, angle theta. Now magnitude remains R, but the angle becomes theta plus phi. So if you want an anti-clockwise rotation, by phi, then you have to multiply e raised power j phi. Okay. So this can be called as the phase shift operator. So for two-phase system, what is the phase shift that we need? 90 degree. If you need a phase shift of 90 degree, then for anti-clockwise, what you will do? E raised power j 90, which is cos 90 plus j sin 90, which is j. If you multiply the voltage by a value j or by iota, then you will get a phase shift of 90 degree in the anti-clockwise direction. What about if we need clockwise rotation? We need minus j 90, because if you take minus phi, then this will become theta minus phi. Theta minus phi means clockwise rotation by an angle phi. Okay. So this will be cos 90, cos of minus 90 plus j sin of minus 90. Cos of minus 90 is 0, sin of minus 90 is minus 1. So minus j. So if you multiply it by minus j, then you will get a clockwise rotation of 90 degrees. Is it fine? So that means this is 90 degree j, then 180 degree j square, then 270 degree j cube, then 360 degree j4. So that is how you can obtain the phase shift. What about three phase? In three phase, we need a phase shift of 120 degrees. So we will multiply by an operator alpha known as e raised power j 120, which is cos 120 plus j sin 120. Cos 120 is minus half, sin 120 is j root 3 by 2. So this will give me anti-clockwise rotation. And if we want clockwise, then we take alpha square, which is equal to e raised power j 240, e raised power j 360 minus 120, 2 pi minus theta is equal to theta minus j 120. So it becomes cos of minus 120 plus j sin of minus 120. Cos of minus theta is same as cos theta. Sine of minus theta is minus sine theta. So it is also equal to alpha conjugate. So if you multiply the value by alpha, we will get anti-clockwise rotation of 120. If we multiply it by alpha conjugate, we get a clockwise rotation of 120. That means if I give you a phasor, let us say first phasor, if you want to generate second, you will multiply 1 into alpha. If you want to generate clockwise third, you will make 1 alpha square. This way we can generate the three-phase phasors having the same magnitude but a phase shift of 120 degrees. Now as I told you, we are mostly focusing on the three-phase systems as they are most widely used. So why three-phase systems or why they are very important? First of all, generation and distribution. Now all over the world, we are generating and distributing the power in terms of three-phase AC. Okay. In US, we use a frequency of 60 Hz. In UK, we use a frequency of 50 Hz. In India, we use a frequency of 50 Hz because we have taken our system from the UK or the Britishers where the frequency of 50 Hz is being used. Okay. So since all the power is being generated into three phase, it is unnecessary to first convert it to single phase and then transmit. So it is better that we use three phase system for transmission. Okay. Otherwise it would be uneconomical. The second reason is that if when we will derive instantaneous power, it comes out to be constant. Okay, like when we derived the power in case of AC, we were getting two terms. One was Vi cos phi. The other was a term which was a function of twice the frequency. So that is when I told you the instantaneous power in AC oscillates at double the frequency as compared to the supply. But here we will get the instantaneous power as constant, which means no vibrations, which is better for the shaft of the machines if there are no vibrations or if there are no oscillations in the power. And the last reason is it is most economical. Why? In three phase, we either use three phase 3 wire or three phase 4 wire. But if you use three single phase, one single phase system requires 2 wire. It implies 6 conductors. So the cost will be higher. Okay. That means we are saving in the amount of copper that we are using, or we are saving in the amount of aluminium in case of transmission line by using the three phase system. Otherwise the same case can be generated from three single phase systems, but the cost will be higher. Now when it comes to polyphase AC or when it comes to three phase, we define a phase sequence. Phase sequence is something which tells us how different phases are shifted from each other. Like first type of sequence is known as positive sequence. Now what is positive sequence? It is given by RYB, or even we can call it as ABC. What does that mean is first R will come, then Y will come, then B will come, then again R. That means RYB can also be written as YBR, can also be written as BRY. Okay. These three combinations correspond to the positive phase sequence. Now when we draw the AC voltages for these, if R is taken as reference, R will be like this. Then Y should come. That is, Y should be lagging by 120 degrees. Then B should come. like this. This is R, Y, B. Okay. So if it is 90, this will be 210 lagging by 120. This will be 330. So this way the three-phase AC voltages will be arranged. If we represent it in terms of phasor, then if R is taken as reference, first R will come, then lagging 120. Lagging means clockwise. There will be Y. Then again lagging 120. There will be B. Or you can say B is leading R by 120. You can either say B is lagging R by 240 or B is leading R by 120 degrees. That is your positive phase sequence. The other type of phase sequence is known as negative phase sequence. When we talk of negative sequence, then we have to interchange two terminals out of 3. That is, let us say RBY, or you can say ACB. That means first R should come, then Y should come, then B should come. Sorry, R, then B, then Y. So what are the possible combinations? RBY, BYR, or YRB. All these three combinations will correspond to the negative sequence. Then how will the voltages be there? First of all, as reference, we will choose R. That is why R is starting from origin. Then we will have B phase starting at 120 degrees. Then we will have Y phase like this. So this is R, B, Y. Same thing we can represent in terms of phasors. If we represent in terms of phasors, then this will be R. By lagging 120, it will be B. And again 120 degree lagging, it will be Y. Or we can say Y leads R by 120 degree. That is how the phase sequence RBY is generated. Is it fine? So these two type of phase sequence we have defined in case of three phase. Now three phase systems are usually categorized into two type of system. One is known as balanced system, other is known as unbalanced system. Now when we talk about a system, there are two type of components. One is a source, other is a load. So a balanced system is the one which has a balanced source as well as a balanced load. Okay. And if any of these condition is violated, either the source is unbalanced or the load is unbalanced, it will be known as the unbalanced system. Okay. Now first of all, what is meant by a balanced source? A balanced source means two conditions. All voltages must have same magnitude or same amplitude. Due to this, or to ensure this, what we do is we keep the windings symmetrical in case of machine. That is, each phase winding must be constructed symmetrically. They must have the same number of turns and they must have the same distribution and the pitch factor. Next is phase shift of 120 degrees. Okay. If the phase shift is 90, 210 or it is, let us say, 150, then it will not be a balanced system. Like if I give you three voltages, VM, sin omega t, Vm sin omega t plus 90, Vm sin omega t plus 120. Then as you can see, between V1 and V2 phase shift is 90 degrees. So it is not a balanced supply. Is it fine? So for a balanced supply, we need a phase shift of 120 degrees between all the three phases. Now when we talk about the balanced supply, there can be two possible connections. One is a star connection and other is a delta connection. In star connection, all the three windings have a common terminal which is termed as the neutral, and the other terminals are R, Y, B. Now as you can see here, to indicate positive sequence, R is like this, then 120 degree clockwise we have placed Y, then 120 degree clockwise we have placed B. That is, windings have been shown in such a manner that I do get the feeling that it is a positive sequence. Now when it comes to three phase, we define two type of quantities: phase quantities and line to line quantities, or also known as line quantities. Now when it comes to voltages, which are the phase voltage? First of all, phase voltage is the voltage across a single winding. Okay, in a three-phase machine, there will be three windings, one corresponding to each phase. So the voltage across each winding will be known as phase winding. So which will be the phase voltages? VRN, then VYN, VBN. Okay. But then we will bring out the three terminals from the machine. These are R, Y and B. If you want to measure the voltage, we need two terminals. So whenever we will apply a voltmeter, it will be between two wires. So what the voltages we will measure? RY, YB, BR. These voltages are known as line to line voltages because these are the voltage between the two lines. Similarly, when it comes to currents, phase current will be the current that flows in each winding. Line current will be the one that flows in these lines. So here the phase current will be IRN, IYN, IBN. Line current will be IR, IY, IB. Now if you see here, IRN will be like this, IR is like this. By KCL I can say the phase and the line currents are same. So remember, for star connection, I phase is same as I line. But yes, line to line and the phase voltages are different. So we need a relationship between the line and the phase voltages. For that, let us draw the phasor diagram. So I'll assume that VRN is reference. Okay. So first we will draw phasor for VRN. Then 120 degree lagging we will draw VYN. Then 120 degree lagging we will draw VBN. Okay. Now if you want to draw VRY, VRY is actually RN minus YN. If you want to subtract two phasors, you have to draw the negative of the phasor and then add it. This is minus VYN. Now if you see, this angle was 120 and this total angle must be 180 because we have reversed the phasor. So this angle is 60 degree. Now if we add these two phasors, what I will get is, I will get the resultant phasor as VRY. Okay. Similarly, if we need YB, then we have to subtract B from Y. Okay, it will be difficult to draw here. So I'll draw directly V B Y. Sorry, Y B. Then if we need B R, we have to reverse R. Then add it to B. If we add it to B, then we will get the resultant phasor VBR. So these are the three line voltages and the three phase voltages. Phase voltages are VRN, YN, BN. This is VRY, BR and YB. These are the three line voltages. Now, as I told you, the condition for a balanced system is all the voltages must have the same magnitude. So the length of VRN is same as length of VYN. If two vectors are equal, the resultant passes midway between them. That is, this angle must be 30 degree. Okay. The resultant of two equal vectors passes symmetrically between the two vectors, or it acts as an angle bisector between those vectors. Okay. So as you can see, VRY lies at 30 degree anti-clockwise with respect to VRN. So it is 30 degree leading. Okay, similarly as you can see here, this will be 30 degree. So VYB is leading VYN by 30 degree. As you see here, this is anti-clockwise 30. VBR leads VBN by 30 degree. So the corresponding line and the phase voltages are with respect to VRN, the corresponding line voltage is VRY. With respect to YN, the corresponding line voltage is VYB. With respect to VBN, the corresponding line voltage is VBR. And the line voltages lead the phase voltages by 30 degrees. But now I need to relate their magnitude. Now VRY was equal to actually Rn minus Yn. Both these voltages has a magnitude of phase V phase, and they were shifted by 60 degrees actually, Rn and minus Yn. So if we talk about mod of VRY and apply parallelogram law, it will be V phase square plus V phase square plus 2 V phase cos 60. I am talking about VRN plus minus VYN. They have a phase shift of 60 degrees. So it is actually under root V phase square plus V phase square, because cos 60 will be half. So it is root 3 V phase. That is, magnitude of line voltage is same equal to root 3 times phase voltage. So what I can write down is V line is equal to root 3 V phase angle 30 degree. That is, in positive sequence, the line voltage leads the phase voltage by 30 degree and its magnitude is root 3 times the phase voltage. Okay. So that is how you define the line voltages. So we are taking VRN as reference. There can be two cases, whether you take the line voltage as reference or phase voltage. So if you are taking VRN as reference and VRY as reference, what are the voltages? VRN, V phase angle 0, VYN, V phase angle minus 120, VBN, BN lags YN by 120, or we can say BN leads RN by 120. So V phase 120, RY, root 3 times phase voltage and it leads the phase voltage by 30 degree. YB, root 3 times phase voltage and leads the phase voltage by 30 degree, that is minus 90. BR, root 3 times phase voltage and leads the phase voltage, which one? BN by 120. Now if you see, the phase shift between the line voltages is also 120 degrees. Okay, that is minus 120, and this is again minus 120, because 150 is actually equal to minus 210. But here if we take VRY as reference, then it will be VL angle 0. Sorry, VRN will be equal to, we can say, V phase angle minus 30, because VRY is taken as reference. So we can say that line voltage leads the phase voltage by 30 degree, or phase voltage lags the line voltage by 30. What about VYN? It will be V phase angle minus 150 degree. VBN, V phase angle 90 degree. Okay. What I have done is, I have added 120 degree to this and subtracted this 120 degree from the VRN. VRY, it will be root 3 V phase angle 0, because it has been taken as reference. VYB, root 3 V phase angle minus 120. VBR, root 3 V phase angle plus 120. Okay. So these are the two set of voltages depending upon what you choose as the reference. Similarly, we can construct the set of negative and the positive, or phase voltage and the line voltage, for the case of negative sequence. For negative sequence, what we do is, again let us choose VRN as reference. Then for negative sequence we will have, or let me draw a bit smaller phasors so that I can accommodate all the voltages. RN, YN, sorry, it will be BN, because now we are talking about negative phase sequence. Then it will be YN. Okay. Now if you want to plot VRY, you will have to take the invert of YN and then add it to RN. Okay. This will be VRY. I can directly say this angle is 30 degree. So as you can see here, it is lagging by 30 degree. Okay. And no need to derive the magnitude. It will be root 3 V phase, because again the same configuration is formed. Two phase voltages separated by 60 degree. Is it fine? If we want to draw VYB, for YB we will take the invert of B, like this, minus VBN. This will again be 60 degree. So their resultant will pass through like this. This is VYB. Actually this angle will be 90 degree. So it is vertically upwards. If we want to draw VBR, we will take the negative of VRN. This will be VBR. Okay. This angle will be 120 degrees. So here also the line voltages will be shifted from phase voltage by 120 degrees. But the concept here is that here the line voltage will lag the phase voltage by 30 degree. As you can see here, this is 30 degree clockwise. This is 30 degree clockwise. So if you change the phase sequence, actually the lagging and the leading angles are interchanged. So that means if I take VRN as reference, then what is VRN? V phase angle 0. VYN, V phase angle 120 degree. VBN, V phase angle minus 120. Okay. As you see, the phase sequences are B, Y. Okay. So we have interchanged the voltages for YN and BN. What is RY? Root 3 V phase angle minus 30 degree. What is YB? Root 3 V phase angle 90 degree. What is BR? root 3 V phase minus 150. So as you can see here the sequence is becoming RY, BR, then YB, because it is also negative sequence. If you take VRY as reference, then Rn will be equal to V phase angle plus 30. Okay, because now the phase voltage will lead the line by 30 degrees. Yn, V phase 150, Bn, V phase angle minus 90, Ry, root 3 V phase angle 0, Yb, root 3 V phase angle 120, Br, root 3 V phase angle minus 120. So that will be the phasor representation of all the voltages. The next type of connection can be delta connection. As you can see here, in delta connections, all the voltages or all the windings are connected in kind of a cycle or in a closed loop. Okay. So here if we talk about the phase and the line quantities, first of all let us talk about voltages. The voltage across this winding is VBR. Okay. The voltage across this winding is VYB. Voltage across this is VRY. It is like this, plus, minus, plus, minus, plus, minus. As you can see, negative of one winding is connected to positive of the other winding. The same voltages will be line voltage RY, YB, BR. That means in delta connection, line and the phase voltages are same, because every winding is actually connected between the two lines. Like if you see this winding, it is connected between R and the B line directly. What about currents? The current in each winding, the first winding current is I, RY, second is I, YB, third is I, BR. But as you can see in the line, the current is IR, IY, IB. So these are not the equal. That means in delta connection, you have to remember phase voltage is same as line voltage. Like in star connection, we had phase current equal to line current. In delta, we have phase voltage equal to line voltage. That means we have to derive the relationship between their currents. Okay. So if you want to derive IR, what will be IR? It will be I RY minus I BR, because RY will be going like this, BR will be going like this, and this is my IR. So IR is equal to I RY minus BR. You can now directly write, because R must be the first subscript and the second current in which it is a second subscript. So IY, the first subscript, Y, so IYB, and the second current should be such that Y should be the second subscript, IRY. IB, first subscript should be B, that is IBR. Then second should be B, IYB. So this is the relation between the phase and the line currents. Now let us plot it over a phasor. So if I take here the voltage VRY, YB and BR. Okay, these are taken as reference because phase and the line voltages are equal. Now current, if we take a lagging load, will lag the voltage by phi angle. So this let me call as IRY, then IYB, then IBR. Let me draw like this. Okay. Now if you need, first of all, IR, it will be RY minus BR. So that means you have to invert BR and then take the sum. So if we invert VBR and then take the sum, it will be like this. Now the angle between these two is 120 degrees. So this angle should be 60 degrees, which implies this should be 30 degrees. Because this is equal to I phase, this is also equal to I phase. As you can see here, this IR is lying clockwise at 30 degree with respect to IRY. That means I line lags I phase by 30 degree. Okay, line current lags the phase current by 30 degree in case of positive phase sequence. What about the magnitude? If two vectors of equal length are oriented at 60 degree, the resultant will come out to be root 3 times, as we derived in case of voltage. So I can directly write I line is equal to root 3 I phase angle minus 30, because it lags the phase current by 30 degrees. Is it fine? So that is the relationship between line and the phase current in positive sequence delta connection. So that means I can write all the currents something like this. IR, it is equal to root 3 times IRY angle minus 30. IY, root 3 times IYB angle minus 30. IB, root 3 times IBR angle minus 30. So they will lag their corresponding phase currents by 30 degree. Like the phase current for IR is IRY, phase current for IY is IYB, phase current of IB is IBR. Is it fine? So again we can write down the phases. If we are taking VRY as reference, then what about IRY? It is I phase angle minus phi. YB, I phase angle minus 120 minus phi. IBR, I phase angle 120 minus phi. Because I am assuming the power factor is cos phi lagging. Okay. Then what about IR? It will be root 3 I phase. It will lag by 30 degree minus 30 minus phi. IY, root 3 I phase minus 150 minus phi. IB, root 3 I phase 90 minus phi. So these will be the angle of the line currents. Same thing we can derive for the negative sequence. For the negative sequence, what is the voltage that I'll assume? RY, then BR, then YB. Now if you again want to derive the currents will lead the voltages by phi angle. IRY, IBR, IYB. Now again if we want to derive IR, it will be IRY minus IBR. If you want to subtract IBR, you will take negative of IBR. And then we will add it to RY. It will be like this, IR. Okay, this angle is 60 degree, so this will be 30 degree. That means if you see now, IR lies at 30 degree anti-clockwise with respect to IRY. That is, IR leads IRY by 30 degree. So in negative sequence, line current will lead the phase current by 30 degree. And the magnitude again will be equal to root 3 I phase, because two vectors of I phase magnitude are oriented at 60 degree. So I can say IR is root 3 IRY angle 30 degree. So that means I can define the angles and the magnitudes of different currents? If we define the angles and the magnitudes, we are taking VR and VRY as reference. So IRY, I phase angle minus phi. IYB, I phase angle 120 minus phi. IBR, I phase angle minus 120 minus phi. IR, it will lead the phase current by 30 degree. 30 minus phi. IY, I phase 150 minus phi. IB, I phase minus 90 minus phi. So these will be all the currents. Sorry, this will be root 3 I phase, all the line currents. So that is how. Okay. So that is the case in delta connection. For positive sequence, lag by 30. For negative sequence, lead by 30. So let us summarize what we have covered in this lecture. First, I told you about the concept of polyphase AC, in which we took an example of two-phase and three-phase. Then I told you about the phase sequence. Then we looked at balanced and unbalanced system. Then we looked at star connection. In star connection, I line equal to I phase, V line is equal to root 3 V phase, angle plus 30 for positive sequence, root 3 V phase, angle minus 30 degree for negative sequence. And last we saw delta connection, in which line voltage is same as phase voltage. IL is equal to root 3 I phase minus 30 for positive sequence and root 3 I phase angle 30 degree for negative sequence. Okay. So this is the most important thing that you must always remember for three-phase systems. In the next lecture, we will continue our study about these three-phase systems. Hi guys, in the last lecture we started with the concept of polyphase AC circuit. There I told you whenever there are multiple voltage sources having the same frequency but different phases, it is known as polyphase. So we saw the example of two-phase system and three-phase system, out of which I told you three-phase system is more dominant, it is more prominently used. Then we took the example of the phase sequence, that there are two phase sequences possible in case of three phase. Positive phase sequence which was RYB and negative phase sequence which is RBY. Then we looked at the characteristics of a balanced and the unbalanced system. I told you a balanced voltage source is one which has all voltage magnitudes equal and phase shift of 120 degree. Mod V is same and phase shift is 120 degrees. Okay. Then we looked at the star connected source, in which I told you line current is same as phase current and line voltage is equal to root 3 times phase voltage, angle plus 30 for positive sequence and root 3 times phase voltage minus 30 for negative sequence. Then we looked at delta connected source. Here line voltage was same as phase voltage, and line current is equal to phase current root 3 angle minus 30 for positive sequence, angle plus 30 for negative sequence. In this lecture, what we'll do is we will study about the loads in the three-phase system, and then we will study various configurations of a three-phase system. Now, I told you a balanced system is one which a balanced system. It should have two things balanced: source and load. Now, what was a balanced source? Where voltage VA, VB, VC all had the same magnitude Vm, but phi A was 0, phi B was minus 120, phi C was plus 120. That is a phase shift of 120 degrees. Then what is meant by balanced load? In the load, we will have load impedance like mod Z angle theta. So, ZA must be equal to mod Z angle theta. ZB must be equal to mod Z angle theta. ZC must be equal to mod Z angle theta. That is, all phase impedance must be equal in magnitude as well as phase. Why is it so? Because if all are equal, then to determine the current, basically you are dividing all the voltages by a same term. Okay? What I mean to say, suppose all the impedances are 2 ohm. Then to derive the current, you will divide all the voltages by 2 ohm impedance. Then all the currents will also have the same magnitude and phase shift of 120 degrees. That is how the currents will be balanced. That means for balanced currents, we must divide the voltages by a constant factor, due to which all load impedances must be equal in magnitude as well as phase. So that is how the condition for the balanced load has been derived. Now, even in the case of load, we can have two connections. One is the star connection. I told you what is a star connection, in which there is a neutral point and then there are three terminals. So for a balanced load, Z1 must be equal to Z2 must be equal to Z3, and since it is a star connection, the line voltage will be equal to root 3 times phase voltage, angle 30 degree for positive sequence, and minus 30 for negative sequence. Okay, and here due to star connection, line current will be same as phase current. But here the direction of the current should be inwards because it is a load. Okay, in case of supply, I showed the current going outwards. Here we have to show the current into the load. The next connection for the load can be delta connection. In delta connected load also, for balance conditions, Z1 must be equal to Z2 is equal to Z3. Since it is delta connection, the line voltage will be same as phase voltage. And how will be the currents? I AB, I BC, I CA. This will be IA. So IA will be equal to IAB minus CA. In the last lecture, I told you the trick to write these currents. First subscript A, second subscript A. IB, IBC minus IAB. Then IC, ICA minus IBC. Okay. And here we have derived in delta connection, line current is equal to root 3 times phase current, angle minus 30 for positive sequence, and line current is equal to root 3 times phase current, angle plus 30 for negative sequence. That is, for positive sequence, line current lags behind the phase current, and for negative sequence, line current leads the phase current by 30 degrees. Now the first kind of configuration that we have in case of three-phase system is source as well as load are both star connected. Okay. Now here, as you can see, we have tied the neutral terminals of both the source and the load. So what is the voltage across this impedance? VR. So IR will be equal to VR by Z, which is same as IRN. As I told you in star connection, the line and the phase current are same. Is it fine? Then what about IY? It will be equal to VY by Z, and IB, it will be equal to VB by Z. If we talk in terms of phasors, for positive sequence VR, VY, VB. Now this will be IR lagging by an angle phi, where phi is the impedance angle. IY, IB. These also have the same magnitude. IR, IY and IB, these have the same magnitude equal to V phase by mod Z. Okay, that is the magnitude of these currents. Is it fine? Now, if we want to find out the neutral current, suppose this neutral is grounded here. This is the neutral current. This neutral current is IR plus IY plus IB. Now remember one thing, whenever there are three phasors of equal magnitude oriented at 120 degree with respect to each other, their sum will always be 0. Because, let me take an example. If one phasor is oriented at 0 degree, let us say, one at minus 120, one at plus 120. Okay. Now this suppose is 1. This will be alpha, 120 degree anti-clockwise rotation. This will be minus 120, so this will be alpha square. 1 plus alpha square. 1 plus alpha is minus half plus j root 3 by 2. Alpha square is minus half minus j root 3 by 2. This gets cancelled out. So it is 0. That means whenever three phasors of equal magnitude, how equal magnitude? You can multiply each of these by amount V. Okay, because mod of alpha equal to mod of alpha square is 1. These are just the phase shift operators and they do not change the magnitude of any quantity. So you can multiply everything by V. So if three phasors of equal magnitude are oriented at 120 degree with respect to each other, their sum is 0. That means in a balanced system, the neutral current is 0. So you can either connect the neutrals with respect with each other, or you can even leave them isolated. Because anyways, the current going through the neutral is 0. Is it fine? Now what we'll do for the further connections is, we will change them to the corresponding star-star connections so that analysis can be easily performed. Because for star connection, I know the voltage across each load, so it is easier to derive the currents. So the next connection is star delta, in which star is the source and delta is the load. Now if you want to convert it to star star, that means we have to change the load to star. When we convert delta to star, like suppose this is Z1, Z2, Z3. If we convert it to star, what is the expression? ZA, ZB, ZC. What is ZA? Z1, Z2 over Z1 plus Z2 plus Z3. Similarly, ZB will be Z2, Z3 over Z1 plus Z2 plus Z3. Similarly, ZC will be Z1, Z3 over Z1 plus Z2 plus Z3. Now, if all are equal, it will come out to be Z by 3, Z by 3. That means when we go from delta to star, we will change each impedance to Z by 3 and the angle of impedance will remain same. So this load will be converted to star. Z by 3, Z by 3, Z by 3. Okay. So that is how you can derive the star star equivalent of the star delta connection, and then you have to apply the same analysis that we done for the star star connection. The next is your delta delta connection. Here we have to transform the source to star also, as well as we have to transform the load to star. We know how the load will be converted to star. We will define new impedance as Z by 3 and directly connect these three impedances in star. Okay, this is Z by 3. Now when you convert these voltages in star, we have to take care the line voltage remains the same. That is, right now if line voltage is VAB angle 0, VBC angle minus 120, VCA angle 120. When we will define the phase voltages, or we will define the phase voltage in the star connection, then also the line voltage should come out to be this same value, so that system is unaffected. So we will define VAN angle minus 30, because in star connection for positive sequence, line voltage must lead the phase voltage by 30 degree. What will be VBN? It will be minus 150 because it is leading by 30 degree. Okay, this VBC is leading VBN by 30 degree. VCN will be 90 degree. Okay, VCA is leading VCN by 30 degree. Okay, so plus 30 plus 30 plus 30. Here phase voltage will be taken as line voltage by root 3. That is how you will derive the phase voltages and the impedance in per phase terms by scaling them to the star star connection. Okay. So here the main objective was that the system must be unaffected or the system voltages must remain same. Is it fine? In the next connection is delta star connection. Here source is delta, so it must be converted to star. The load is already in star. So again what we will do? VRN will be VR by root 3 angle minus 30, VYN VY by root 3 angle minus 30. Why I am writing both angles as same? Because this is angle with respect to VY. VYN will lag VY by 30 degree because VY will have itself certain angle. So you can write it like this: VL by root 3 angle minus 30, because phase of VR will be 0 but phase of VY will be minus 120. So it will be VL by root 3 angle minus 150. Minus 30 from here, minus 120 from VY. What about VBN? VB by root 3 angle minus 30. The phase of VB will be 120. Then minus 30 will give me 90. So these are the phases of the three voltages. That is how you will find the star equivalent of the delta connected source. So these are the simple configurations which are generally encountered in a three-phase system. Okay, and the benefit with the star connection also that we have is that if you have certain line impedance, the line impedance of the line connecting the source to the load, in case of star connection that comes in series with the load, so that can be directly added with the load. Is it fine? Because if you see here, if I give you certain impedance here like Z1, this Z1 and Z will be in series. So it is easier to solve such kind of networks. And the beauty of balanced system is that here you need to solve only on one phase, which is also known as per phase equivalent. Because we know in a balanced system, all the phase voltage and all the phase currents are displaced from each other by 120 degrees. So if we derive the solution for one phase, we can derive the other phases just by shifting each phase 120 degrees. That is why the analysis becomes easier even in case of subjects like machines and power system if the system is balanced. Now let us see how we can define the power or how we can derive the power in a three-phase system. Now, assuming balanced system. So let me define the voltages. V phase sin omega t, V phase sin omega t minus 120, V phase sin omega t plus 120. What about IR? V phase by mod z sin omega t minus phi, let us say lagging, or I will say I phase sin omega t minus phi. What about IY? I phase sin omega t minus 120 minus phi. IB I phase sin omega t plus 120 minus phi. Now what we have to do is we have to find the power. So instantaneous power will be VRN IR, VYN IY, VBN IB. We will multiply voltage with current and then we will take the sum over all the three phases. That is V phase, I phase. Now when it is sin omega t multiplied by sin omega t minus phi, we can take the expression for sin C sin D. 2 sin C sin D is cos of D minus C, that is cos of phi minus cos of C plus D. 2 omega t minus phi. Okay. Similarly about the other terms, when you will do D minus C, it will be cos phi and then C plus D will be 2 omega t minus 240 minus phi. Here 2 omega t plus 240 minus phi. So if we write down the entire expression, in each power we will get two terms, V phase, I phase. The first will be V phase, I phase by 2 cos phi cos 2 omega t minus phi plus V phase, I phase by 2 cos phi minus cos 2 omega t minus 240 minus phi plus V phase, I phase by 2 cos phi minus cos 2 omega t plus 240 minus phi. Now if you see the second term in each of the power expression, the first one is located at an angle minus phi. If this is the reference, this is at minus phi. Then the next one is at minus 240 degree to this. Minus 240 means plus 120. This is 90, 120. This will be like this, somewhere like this. Okay, that is at 120 degrees anti-clockwise, or you can say 240 clockwise. Other will be like this. Okay, this will be at 120 degrees to this. Now I told you whenever three phasors of equal magnitude and phase shift 120 degrees are located with respect to each other, their sum is 0. That means these three terms will amount to a 0 sum. So what will be the total power? The total power will be due to the first terms only, 3 by 2 V phase I phase cos phi. That is what I told you, that the sum, or we can say the instantaneous power, is constant, it is not fluctuating. But when we were considering only single phase, this term was appearing, that is the power was oscillatory or the power was pulsating. But in three phase, even the instantaneous power is constant, which is definitely an advantage. Now these are the maximum values. So it can be written as 3 Vrms per phase Irms per phase cos phi. Okay, that is your power in case of 3 phase. Now if you consider a star connection, V phase RMS will be VL RMS by root 3. So it will become VL RMS, and we know I phase is equal to IL RMS cos phi. If it were delta connection, then V phase will be equal to VL, but I phase will be equal to IL by root 3. Okay, so the same formula will result. So the formula remains the same for star as well as delta connection, 3 V phase I phase cos phi or root 3 VL IL cos phi, where phi is the power factor angle, or you can say it is the load impedance angle. So let us summarize what we have covered in this lecture. We first saw the concept of balanced load, in which we saw two types of load, star connected and delta connected. Then we saw the connection for the three-phase system, that is star star, star delta, delta star, delta delta, in which I told you to convert each system to an equivalent star star connection so that you can easily derive the output. Then we saw the power, which was 3 V phase I phase cos phi. Mind you, here I am using the RMS values, or root 3 VL IL cos phi. That is your power in the three phase. What will be the reactive power? Similarly, the reactive power will be 3 V phase I phase sin phi, or we can say root 3 VL IL sin phi. That will be your three phase reactive power. So this is all about the basics of the three phase system that you need to understand, as you may not get a direct question from this topic, but this is the prerequisite for many other subjects. Hi guys, in the last few lectures we have focused on the concepts of the three-phase system, as to how to analyze three-phase system, what are various configuration of the three-phase system. In this lecture what we'll do is, we will take a look at what kind of problems can be framed on the three-phase system. Now looking at the first problem, it is asking VAN, VBN and VCN are the three phase voltages of a system. VAN has been given to me. VAN is 100 angle 30 and VCN is given to me 100 angle minus 90, which can be written as 30 minus 120, which means VCN lags VAN by 120 degree. Okay. If VCN is lagging VAN by 120 degree, then the phase sequence is A, then C, then B will come. So it is a negative phase sequence. Okay. So that is how you need to determine the phase sequence, and remember one thing. It is not necessary that you will define the phase sequence only in case of balanced system. Even if I give you 3 voltages, something like this, if 3 voltages are like this, VAN 100 angle 30, CN 100 angle minus 60, BN 100 angle, let us say minus 60, so it is minus 90, then let us say minus 120, let us say this. Then here it is a phase shift of minus 90, minus 120. Still the phase sequence is A, C, B. Okay. Phase sequence just indicates which the voltages lie in what sequence. Doesn't matter what is the phase shift. In the next problem, it is asking, in the figure, a balanced three-phase star connected source with a positive phase sequence is given to me. What is the voltage VBC? Now, VAN is equal to 390 angle 30. What will be VBN due to positive sequence? 390 angle 30 minus 120, that is 390 angle minus 90. VCN 390 30 plus 120, that is 390 angle 150. Now what is VAB? Root 3 390, and in positive sequence the line voltage leads the phase voltage by 30 degree. 30 plus 30, that is 675.5 angle 60 degree volt. What is VBC? VBC will lag VAB by 120 degree, that is 675.5 angle minus 60 degree volt. That will be your VBC. Similarly, VCA, it will still be 120 degree lagging. That means 675.5 angle minus 180 degrees. Okay. Moving on to the next problem. It is saying in the three-phase circuit shown in the figure, the loads are balanced. That is, all load impedances are equal in magnitude as well as phase. So Z is given to me as 12 plus J5. We need to find the magnitude of phase current and line current. Here I have been given the line voltage as 400 angle 0. So if VAB is 400 angle 0, what is VAN? 400 by root 3 angle minus 30 degree. Okay, that is my VAN. Now, if you want to calculate IA, it will be VAN by Z. That is 400 by root 3 angle minus 30 by 12 plus J5. Okay, so it will come out to be 17.76 angle minus 30 minus tan inverse 5 by 12. Okay, but since we are interested in only the magnitude, so phase current magnitude is 17.76 ampere, and since it is a star connected load, it is also equal to the line current. Is it fine? So remember, whenever we are given a star connected load and the line voltage is given to me, first you need to convert it to phase voltage, and then you can make use of that voltage to determine the current. In the next problem, it is asking, in the three-phase circuit shown below, we need to again find magnitude of line and the phase current. Here if you see, it is a delta connected load. So actually line current is root 3 times phase current. But here phase voltage is same as line voltage. So what is the phase voltage? 400 volt. What is the phase current? Phase voltage by impedance, that is 400 by 10. So it is 40 ampere, which means line current will be root 3 times 40, which comes out to be 69.3 ampere. Since we are talking about only the magnitude, I am not considering any angle of the impedance. If you were considering the angle of impedance, here the phase current will lag the phase voltage by 60 degrees. Okay, that is, if I give you as 400 angle 0, then I phase or current in this branch will be 440 angle minus 60, this way. But since ABC are not given to me, I cannot say about the other currents. I do not know their sequence. Okay, So that means the angle can only be asked in a problems where you will be given the terminal naming. In the next problem, it is saying in the following three-phase circuit, the line currents IA, IB and IC are equal to. It is the case of a star-star connection. That means IA will simply be 400 angle 0, that is the phase voltage, divided by the impedance, that is equal to 400 by 4 root 2 angle 45 degree. That is, current is leading the voltage. So it is 100 by root 2. 100 by root 2 becomes 100 root 2 by 2, that is 70.7. What about IB? Since it is a balanced system, IB will lag IA by 120 degree. 45 minus 120 will be 70.7 angle minus 75 degree. What about IC? It will lead IA by 120 degree. So it is 70.7 angle 165 degree ampere. So these are my line currents as well as the phase current because it is a star connection. In the next problem, it is asking us about a balanced delta connected load is connected to a balanced star connected load. Okay, so it is a delta star type of connection. In this, what we did, we transformed the source from delta to a star equivalent and then we used that value in order to determine the phase and the line currents. Okay. So now we have been given VAB as 400 angle 0. What is VAN? It will be 400 by root 3 angle minus 30 because in positive phase sequence, phase voltage will lag the line voltage by 30 degree. What about the impedance? It is 80 plus J50, which if expressed in polar form is 94.3 angle 32 degree ohm. So what is the line current IA? 400 by root 3 angle minus 30 divided by 94.3 angle 32. So this comes out to be 2.44 angle minus 62 degree ampere. Now I know IA. I can calculate IB easily. It will lag IA by 120. 2.44 minus 182 degree ampere. IC will lead IA by 120. 2.44 angle 58 degree ampere. Okay. That is the beauty of a balanced three-phase system. You just have to solve for one phase and the results for the other phase can be obtained by phase shifting of 120 degrees. In the next problem, it is saying a balanced star connected load absorbs the total power of 20 kilowatt. So power is given to me as 20 kilowatt. Okay. So this will be power factor. Power factor is given to me as 0.6 leading when connected to a line voltage 480 volt. What is the impedance of each phase? Now I know power is equal to root 3 VL IL cos phi. Okay. So 20 into 10 raised power 3 root 3 480 IL into 0.6. So what will be the line current coming out to be? 40.09 ampere, which is same as phase current because it is a star connection. So what is magnitude of Z? It is V phase by I phase. Okay, remember always the impedance is defined on per phase basis. So you have to take the ratio of phase voltage to the phase current. Now phase voltage in case of star connection is line by root 3. When divided by phase current 40.09, it will come out to be 6.91 ohm. But still we do not know the angle. Now as the power factor is leading, that means the impedance must be capacitive. Capacitive impedance means negative angle. 6.91 angle minus cos inverse 0.6. Okay, negative because it is capacitive. 6.91 angle minus 53.13 degree ohm. Because in capacitive, impedance will be R minus jXc. So that is, the angle will be negative. In the next problem, it is asking us to use the Thevenin equivalent circuit and derive the RMS value of current in 100 ohm resistor. Now, for Thevenin equivalent circuit, we need two things: open circuit voltage and Thevenin resistance. Till the switch is open, this system is a balanced system. If this system is balanced system, what is the voltage across this 300 ohm resistor? Okay. Actually, I think, okay, this is given to me. 400 by root 3. So what is the phase voltage? 400 by root 3 volt. That will become my open circuit voltage. Now I know the open circuit voltage. Now we need to determine the Thevenin resistance. For that, we will short circuit the voltage sources. If I short circuit the voltage sources, this terminal is already common between the impedances. This terminal becomes common due to shorting. So all these impedances become in parallel. As I told you, one of the necessary condition for parallel connection is that the impedances must have two terminals in common. One terminal was already common due to the neutral connection. Other becomes common because of the shorting of the supply. So when three 300 ohm resistors are connected in parallel, what will be the Z Thevenin? It will be 300 by 3, which is equal to 100 ohm. Okay. Now I know open circuit voltage as well as the Thevenin resistance. So 400 by root 3, then 100 ohm, then again 100 ohm. So what is the RMS value of current? 400 by root 3 divided by 200, which comes out to be 2 by root 3, which comes out to be how much? 1.15 ampere. That is the RMS value of current across the 100 ohm resistor. What is the RMS value of voltage? IR, that is 115.5 volt. Okay. So that is how you can find out the voltage. In our last problem, it is saying a 230 volt phase 50 hertz 3 phase 4 wire system has a phase sequence ABC. Now we have been given a unity power factor load. Unity power factor load means resistor in the phase A and neutral N. So let me assume the reference as VAN. 230 volt is the voltage. 230 angle 0. 230 angle minus 120. 230 angle 120. Okay. Now it is asking us to achieve zero neutral current through the use of a pure inductor and pure capacitor in other two phases. But it is not telling us what is to be connected in which phase. So I am assuming inductor is connected in phase B, capacitor is connected in phase C. Okay. So what is the impedance of inductor? JXL. For capacitor it will be minus JXC. Now I can directly calculate because the power is given to me 4 kilowatt and the voltage is 230. So it comes out to be 17.391. Angle will be 0 because it is a resistive load. Current and voltage are in same phase. Now as I told you, the neutral current is actually equal to sum of all the currents. So it is saying that sum of the currents is 0. Do not think that zero neutral current implies a balanced system. A balanced system implies the zero neutral current. Okay. So the converse is not true because as you can see here, one phase has a pure resistor, other has a pure inductor and the third one has a pure capacitor. Definitely it is not a balanced system, because in a balanced system the three impedances are identical. Okay, so do not go to a conclusion that it will be balanced and then solve it. It is actually a unbalanced system. Now IA I know 17.391 angle 0. We have connected inductor in phase B. So 230 angle minus 120 by, if inductor is connected in phase B, it will be XL angle 90. If capacitor is connected in phase C, XC angle minus 90. This should be 0. Okay. So 17.391 angle 0, 230 by XL angle minus 210 and 230 by XC angle 210. This will come out to be 0. Now if a complex number is 0, that means real as well as imaginary part is 0. So separating the real and the imaginary part, 230 by XL cos 120 plus 230 by XC cos 120, sorry, cos 210 okay, plus J minus 230 by XL sin 210 plus 230 by XC sin 210. If you equate the imaginary part to 0, it implies 230 by XL sin 210 is equal to 230 by XC sin 210, which implies XL is actually equal to XC. That is, their reactances are same. Now if we focus on the real part, 17.391, 230 by XL, I will multiply it by 2 cos 210. Okay, why I have multiplied by 2? Because XL equal to XC. 17.391 plus 460 by XL cos 210 is minus root 3 by 2. So from here if we derive XL, XL will come out to be 22.9 ohm. Okay, since this value is greater than 0, that means our hypothesis is correct. That means inductor will be in phase B, capacitor will be in phase C. If this value was negative, then JXL will be less than 0, that means it is a capacitor, and minus JXC will be greater than 0, that means it is a inductor. That means we have misplaced the capacitor and inductor. Inductor should be in phase C and capacitor should be in phase B. Okay. Now we know XL equal to omega L. So from here I can calculate L. 22.9 by omega, that is 100 pi. So it is 72.9 millihenry. And 1 by omega C is also 22.9. So C will be 1 by 100 pi 22.9. It will be 138.9 microfarad. Okay. So that is how you derive the inductance and capacitance. So these sort of problems can be most commonly asked, but usually you cannot see an isolated problem on a three-phase system. It will be used in conjunction with your other subjects, like the case of machines and the power system. So this is all from the three-phase systems. Hi guys, in this video I'll be discussing with you all the concept of locus diagram in network analysis. Okay, so what we will be discussing is the locus diagram. Now what is our meaning of a locus? Locus is nothing but it is a path traced by a certain point. Okay, Like if I take an equation x square plus y square equal to r square, we know that this is the equation of a circle. Or we can say the locus is a circle, that is the point traces a circular path about origin. Is it fine? So locus is nothing but it is a path traced by a certain point as per a certain equation. Now locus diagram in network analysis is used to find the path traced by the tip of a phasor diagram or tip of a phasor. So it is in locus diagram in network analysis is the path traced by tip of phasor. Now this concept is very much similar to what we study in control system by the name of polar diagram or polar plot. It is very much similar to that. Okay. But I won't be able to explain you directly, so let me take an example and then you will better understand how to draw the locus diagram and also what information does it give. So let us take a RC circuit. Okay. So it is being excited by an AC voltage source RC. Suppose I am interested in finding the tip of the current phasor diagram. This is Vm sin omega t, where your omega is variable. Okay. If omega is variable, then first of all, you want the locus of I. So what I'll do is, I'll find out the phasor of the current. It is Vm angle 0, that is a voltage phasor, divided by the impedance. Okay. Which means j omega c Vm by 1 plus j omega RC. Now just like the polar plot, you have to break this equation into two parts, that is the magnitude. When you take magnitude, it will be omega c Vm over under root a square plus b square omega square r square c square. Also the phase of numerator is 90 degree and the phase of denominator is tan inverse omega RC. Now based on this information, so let me write down here, magnitude is omega c Vm by under root 1 plus omega square r square c square, and phase is 90 minus tan inverse omega RC. Based on this information, I have to plot the polar plot, or you can say the locus diagram. So what I'll do is, I'll make a table having three columns. One is the frequency which is being varied, other is the magnitude and phase. Suppose omega is 0. If you put 0 in the denominator, it will be 1, but 0 in the denominator will give me 0. Tan inverse 0 will be 0, so 90 minus 0 is 90. Suppose 1 by RC I take. 1 by RC, the denominator will be 1 by root 2. So it will become 1 by RC into CVM by root 2. You can say Vm by under root 2 R. Okay. So Vm by root 2 R. At 1 by RC, omega RC will be 1. Tan inverse 1 is 45. 90 minus 45 is again 45. What about infinity? For infinity, what you have to do is limiting omega tending to infinity, omega c Vm by under root 1 plus omega square r square c square. Taking out omega common, CVM 1 plus omega square plus r square c square. As omega tends to infinity, 1 by omega square tends to 0. So CVM by RC, that is Vm by R. At infinity, tan inverse is 90. 90 minus 90 is 0. Now based on these phase, what I can say, that this plot lies in the first quadrant. Okay. Now I think you will be very well knowing these angles. This angle is 0 degree, 90 degree, 180 degree. Similarly, minus 180 degree, minus 90 degree and 0 degree. Now initially the magnitude is 0. Okay. So it is at this point. And phase is 90, means along the vertical axis. Finally, the magnitude is Vm by R and phase is 0. So it will go like this. This magnitude is Vm by R. That is, if you draw a current phasor, as you vary the omega equal to 0 to infinity, the tip will trace this path. It will go over this semicircle type of figure. It is not exactly semicircle, so don't call it semicircle. It is like a semicircle but not exactly same as semicircle. So it will go over this path, and that is called as your locus diagram. Let us take one more example. Okay. Now, again in the same circuit, suppose I say instead of omega, R is variable. So what was the current expression? J omega C Vm by 1 plus j omega RC. Or we can say the magnitude was omega C Vm 1 plus omega square R square C square, and phase was 90 minus tan inverse omega RC. Now again I will make a table, but this time the independent variable would be R, then magnitude, then phase. Suppose R is 0. If R is 0, the denominator would become 1 in the magnitude. It will be omega C Vm and phase will be 90 degree. If R is infinity, the denominator would become infinite but numerator will be constant, so it will be 0. Tan inverse infinity is 90, 90 minus 90 is 0. Again, by looking at the phase, what I can say is the first quadrant. Okay. So I'll try and draw the locus diagram again. So initially at 0, its length is omega C Vm and phase is 90 degree. And at infinity it goes to origin because the magnitude becomes 0. So it will be somewhat like this. That is, the tip of the current will follow this circle or semicircle. Okay. Again, it is a semicircle type of figure, not exactly a semicircle. So it will go over this figure. Is it fine? So that is how you draw the locus diagram. Let us take one more example. Let me take an RL circuit. Now let me say this resistance is variable, this is inductance, this is our source Vm sin omega t. Okay. Let me say this is current I. Now I want to draw the phasor or the locus diagram of VR. VR can be derived from voltage division. The supply is Vm angle 0 into, we are talking about VR, into R by R plus j omega L, directly voltage division. Now what about the magnitude? The magnitude will be Vm R by under root R square plus omega square L square. What about phase? Phase, the phase of numerator is 0 minus tan inverse omega L by R. Now since your R was variable, you will again make a table. R, magnitude and phase. When R is 0, here when R is 0, the numerator is 0 but denominator is non-zero, so magnitude will be 0. When R is 0, tan inverse infinity 90 because of minus sign, minus 90. When R is infinite, what you will do, limiting R tending to infinity, VMR by under root R square plus omega square L square. That is limiting R tending to infinity, Vm by under root 1 plus omega square L square by R square. That is Vm. What about phase? When R is infinite, tan inverse 0 is 0. So 0 degree. Now based on these angles, what I can say that the figure will lie in fourth quadrant, and due to this fourth quadrant, what I'll do is initially it is at 0, then it goes to 0 degree but at Vm, somewhat like this. This length is Vm and initially it is along minus 90 degree line. Okay, so that is how you guys can plot the locus diagram. So let me outline the steps involved. So step 1, determine the expression of phasor whose locus diagram is to be drawn. Step 2, find magnitude and phase. Step number 3, find m and phi at 0 and infinity, that is the parameter is 0 and infinite. Step 4, plot on a polar plane. Okay, if you do these steps you can always draw the locus diagram, but first and the most important step is deriving the value of quantity whose locus you will be drawing. Okay, if you are clear with that, then you can basically draw. Is it fine? So that is how you draw the locus diagram. Now you can try the problems that have been asked in previous year. There are 2-3 problems that have been asked, and now I think they will seem trivial to you. Thank you.